The ancient world is filled with structures that seem to exist in the wrong place in history. Massive underground complexes built long before modern excavation tools. Precision stonework appearing in civilizations separated by oceans. Cities designed around astronomical events that repeat only at specific moments in the sky. What makes these places mysterious is not just their age, but the feeling that parts of their story are still missing. In many cases, archaeologists know what was built, but not why it was built that way, why it was abandoned, or why similar ideas appear in distant cultures with no obvious connection. The ruins remain physically real and scientifically measurable, yet the deeper researchers investigate them, the less complete the ancient world begins to feel. Beside the Atlantic coast of Portugal, the Roman ruins of Troy preserve the remains of what may have been one of the most technologically advanced industrial cities of the ancient world. Salt, humidity, sea erosion, bacteria, and nearly 2,000 years of Atlantic storms should have destroyed the site long ago. Instead, parts of its factories, drainage systems, food processing tanks and thermal engineering structures still survive. What archaeologists uncovered here was not just a Roman settlement, but an enormous technological experiment that modern science still struggles to fully explain. The ruins of Troy were first documented during the 16th century, but systematic excavations only began in the 19th and 20th centuries. Archaeologists uncovered massive fish salting factories, Roman baths, villas, mausoleums, and industrial infrastructure buried beneath coastal sand dunes. What shocked researchers most was the scale of the site. More than 25 industrial salting tanks were identified alongside evidence of long-distance trade routes that once connected this Atlantic outpost directly to Rome itself. Yet, the deeper excavations went, the stranger the city became. Most Roman cities were organized around politics, religion, or military defense. Troy was different. Its economy revolved almost entirely around industrial food production. The city specialized in garum, a fermented fish sauce so valuable that it was traded across the Roman Empire almost like liquid gold. Ancient Roman texts describe premium garum being sold at prices comparable to luxury perfumes. But Troy was not a small fishing village. Archaeologists estimate that its production capacity rivaled some of the largest industrial centers in the Mediterranean world. The factories processed enormous quantities of fish using giant stone vats lined with waterproof mortar. Many of these vats remain structurally intact today despite nearly 2 millennia of exposure to salt air, humidity, and violent Atlantic weather. That alone presents a major engineering mystery. Modern reinforced concrete exposed to marine environments often begins deteriorating within 50 to 100 years as chloride ions penetrate the material, corrode internal structures, and trigger cracking. Yet the Roman mortar at Troy resisted these conditions for almost 2,000 years. Scientific studies on Roman marine concrete from sites such as Portus Cosenus discovered the formation of rare mineral crystals called aluminous tobermorite. These crystals strengthen over time when exposed to seawater. Researchers believe Roman engineers accidentally or intentionally created a material capable of self-reinforcement through chemical reactions with salt water. What makes Troy even more puzzling is geography. Unlike regions near Naples, Portugal had limited access to volcanic ash, one of the essential ingredients in Roman hydraulic concrete. This raises difficult questions. Did Roman ships transport volcanic material thousands of kilometers across the empire? Or did local engineers develop an alternative formula now completely lost to history? Salt is one of the most destructive forces in coastal environments. It expands inside microscopic pores in stone, traps moisture, accelerates cracking, and slowly destroys structures over time. At Troia, however, many walls, drainage channels, and industrial basins remain astonishingly preserved despite direct Atlantic exposure. Some sections still display sharply defined masonry lines, bonded mortar joints, and functioning drainage systems after centuries underground. This unusual preservation has become a serious research topic among material scientists. Comparisons between Troia and Roman harbour structures at Caesarea Maritima revealed similar chemical signatures in surviving marine mortar. Both appear to contain complex mineral reactions involving lime, seawater, and silicate-rich aggregates. Modern researchers from institutions including MIT and the University of Utah have spent years studying Roman concrete because its durability frequently surpasses modern equivalents. Some experimental recreations even suggest Roman concrete becomes stronger over decades instead of weaker. If this interpretation is correct, the implications are enormous. Modern coastal cities spend billions of dollars repairing marine infrastructure damaged by saltwater corrosion. Roman builders may have partially solved that problem nearly 2,000 years ago using chemistry modern engineering only recently began to understand again. The Atlantic coastline creates unstable environmental conditions involving humidity fluctuations, salt-laden winds, and rapid temperature changes. Yet Troia's industrial district appears carefully engineered to regulate airflow, humidity, and temperature. Archaeologists discovered sophisticated drainage systems beneath factory floors, ventilation corridors between processing zones, and carefully oriented structures designed around prevailing ocean winds. Several villas and industrial buildings also contained hypocaust systems, the famous Roman underfloor heating technology normally associated with elite bathhouses. At Troia, however, these systems may have served industrial purposes as well. Some researchers believe heated airflow helped regulate humidity levels during food processing and storage. Others suggest underground air circulation reduced bacterial contamination inside enclosed spaces. These principles resemble passive climate control techniques used in modern, sustainable architecture. Even more surprising is the overall layout of the city itself. Many processing areas were positioned to minimize direct afternoon sunlight while maximizing cross-ventilation from Atlantic breezes. This suggests Roman planners at Troia may have possessed a far deeper understanding of local microclimates than historians once believed. In many ways, the city functioned almost like a carefully calibrated environmental machine. Among all the enigmas surrounding Troia, the food preservation system may be the most astonishing. Garum production was extremely dangerous if poorly controlled. Fermented fish can rapidly become toxic due to bacterial growth, unstable temperatures, and contamination. Yet Troia operated enormous production facilities continuously for centuries. Archaeologists discovered that the salting tanks were not arranged randomly. Their positioning appears highly deliberate and scientifically planned. Some vats were deeper than others depending on the fish species processed inside them. Narrow channels between tanks allowed controlled drainage and airflow. Waste systems prevented cross-contamination between production zones. Even the orientation of the tanks mattered. Several were angled specifically to reduce direct sunlight exposure during the hottest hours of the day, helping stabilize internal temperatures and slow bacterial overgrowth during fermentation. Chemical residue analysis revealed traces of resins and organic compounds coating parts of certain tank interiors. Researchers suspect these coatings may have acted as primitive antibacterial barriers designed to reduce spoilage. If correct, this would mean Roman engineers developed a large-scale food preservation system, combining salt concentration control, airflow regulation, temperature management, moisture stabilization, antibacterial coatings, and sanitation infrastructure centuries before modern microbiology existed. In other words, Troia may have functioned using principles surprisingly close to modern industrial food safety systems. The scale of the operation makes the mystery even more extraordinary. Experimental archaeology suggests some Roman salting factories process several tons of fish annually. Maintaining safe fermentation at that scale without refrigeration should have been extraordinarily difficult. Yet products from Troia travelled across vast distances of the Roman Empire without widespread evidence of spoilage. Some historians compare the complexity of Troia's production chain to medieval industrial systems that would not emerge again in Europe for more than 1,000 years. The city may have been far more technologically advanced than the word ancient usually implies. Another mystery at Troia is the presence of wealthy Roman villas directly beside massive fish processing factories. In most ancient cities, industries producing strong odours were separated from elite residential areas. Yet Troia's villas contained mosaic floors, heated baths, imported marble, and advanced plumbing systems only meters from industrial production zones. Some historians believe garum production created enormous wealth, allowing factory owners to live beside the industry controlling their fortunes. Others suggest something even more unusual, that Troia's ventilation and environmental engineering systems were advanced enough to reduce odours and improve sanitation far beyond what archaeologists once believed possible in the Roman world. If true, Troia may have been one of the earliest integrated industrial cities in human history, operating centuries ahead of its time. What do you think really made Troia disappear? Climate change, collapsing trade routes, or a forgotten disaster? Share your theory in the comments below. Choqquequirao sits nearly 3,050 meters above sea level in the Peruvian Andes, hidden behind steep cloud forests and cliffs that drop hundreds of meters into the Apurimac Canyon. Often called the sister city of Machu Picchu, Choqquequirao is far more isolated, harder to reach, and in many ways more mysterious. What terrifies archaeologists is not its beauty, but the possibility that the Inca engineered an entire mountain itself. Spanish explorers mentioned ruins in the region as early as the 18th century, but Choqquequirao remained largely unknown to the outside world until systematic surveys began in the late 19th and early 20th centuries. Modern excavations accelerated only in the 1990s, and even today researchers believe barely 30 to 40% of the site has been uncovered. LiDAR scans and satellite imaging suggest massive sectors of the city still lie buried beneath dense Andean vegetation. The known complex already covers more than 1,800 hectares, when including surrounding terraces and infrastructure, potentially rivaling or exceeding the broader engineering footprint of Machu Picchu. Hundreds of terraces, ritual plazas, canals, stairways, storage sectors, and ceremonial structures stretch across impossible slopes. Unlike Machu Picchu, which became globally famous, Choqquequirao remained isolated for centuries because reaching it requires a brutal multi-day trek through extreme elevation changes. That isolation may be exactly why the city survived. The greatest mystery of Choqquequirao is not its temples, but the mountain beneath them. The entire city was constructed on unstable slopes vulnerable to earthquakes, erosion, seasonal flooding, and landslides. Modern engineers know that building large stone structures on gradients exceeding 50 or 60 degrees is extremely dangerous. Yet the Inca transformed these slopes into stable architectural platforms capable of surviving for over 500 years. The terraces of Choqquequirao were not simple agricultural steps. They functioned as a giant geotechnical stabilization system. Each terrace was built using multiple engineered layers. Large foundation stones formed the base. Gravel and permeable rock created drainage layers above, and fertile soil was placed on top. This design allowed rainwater to rapidly filter downward instead of building destructive hydrostatic pressure behind retaining walls. The science behind this is astonishing. Hydrostatic pressure is one of the primary reasons retaining walls collapse. When water accumulates behind a structure, the lateral force increases dramatically until failure occurs. Modern retaining systems solve this problem using drainage pipes, gravel backfill, and pressure release engineering. The Inca appear to have discovered the same principles centuries earlier without written mathematics, steel reinforcement, or industrial tools. Researchers studying Inca terraces found that some could drain several times faster than natural mountain soil. During heavy Andean rainfall, this prevented catastrophic slope saturation. Even after centuries of earthquakes and storms, many terraces remain almost perfectly aligned. This becomes even more disturbing when compared with modern failures. In 2017, landslides triggered by extreme rainfall devastated parts of Peru and Colombia, destroying roads and reinforced concrete infrastructure despite modern engineering technology. Yet many Inca terrace systems, including those at Choqquequirao, remained standing. Some engineers have openly admitted that the Inca understood mountain hydrology with extraordinary sophistication. The retaining walls themselves also reveal impossible precision. Certain walls lean inward at carefully calculated angles, increasing stability against seismic activity. Similar anti-earthquake principles appear at Sacsayhuaman and Machu Picchu, where polygonal stone blocks interlock tightly enough to resist movement during tremors. But Choqquequirao is even stranger because of the terrain. The city was effectively carved into a living mountainside. Instead of forcing geometry onto nature, the Inca adapted every terrace to the natural curvature of the mountain. The entire landscape behaves like a gigantic engineered organism designed to absorb stress. No blueprints survive explaining how this was calculated. No written records describe the measurements. And no one fully understands how an empire without iron tools created one of the most resilient mountain stabilization systems in ancient history. Another mystery involves transportation. Choqquequirao sits in one of the harshest environments the Inca ever built in. Massive granite and andesite blocks had to be moved through narrow mountain trails with deadly cliffs on both sides. Some stones weigh multiple tons, yet the Inca had no wheeled vehicles, no horses, and no iron machinery. Even modern hikers struggle to carry basic supplies through the canyon system surrounding the site. The most accepted theory is that thousands of workers dragged stones using braided plant fiber ropes and wooden leverage systems, but many archaeologists argue this explanation is incomplete. Certain construction sectors are positioned on slopes so steep that transporting heavy blocks without fatal accidents would have been nearly impossible. Experiments with reconstructed Inca rope systems show extraordinary tensile strength, but they still do not fully explain how precise positioning was achieved on unstable terrain. Some researchers suspect temporary earthen ramps may once have surrounded sections of the site before later eroding away, while others believe the Inca used sophisticated force distribution methods lost to history. The mystery becomes even greater when comparing Choqquequirao with Roman construction. The Romans possessed cranes, pulleys, iron tools, wheeled transport, and large animal labor forces. Yet many Roman mountain roads and retaining systems collapsed long ago under environmental stress. Meanwhile, numerous Inca structures built with far simpler technology still survive in active seismic zones. One of Choqquequirao's strangest features lies on the ceremonial terraces facing the canyon. Embedded into dark stone walls are giant white llama figures made from bright quartzite rock. These mosaics are enormous and visible from distant slopes across the valley. Archaeologists have identified more than 20 llama-shaped figures integrated directly into the terrace system. Their purpose remains unclear. Some scholars believe they represented caravan routes linking the Andes to Amazonian trade networks, while others think they had astronomical or ritual meaning connected to sacred mountain worship. What makes them mysterious is their durability. Quartzite fragments were inserted into retaining walls exposed to centuries of rain, erosion, earthquakes, and biological growth, yet many remain intact. The stones were positioned with such precision that large sections resisted collapse despite the instability of the surrounding mountain. This suggests the decorative system was engineered simultaneously with the terraces themselves, rather than added later. In other words, even the artwork was part of the structural design. Water management at Choqquequirao may be as advanced as its terraces. The city contains canals, fountains, drainage channels, and hydraulic gradients, engineered with remarkable precision. If the slope angle of a canal is too steep, flowing water erodes the channel walls. If too shallow, stagnation occurs. Modern hydraulic engineering depends heavily on mathematical calculations to avoid these problems, yet the Inca somehow achieved stable water flow across steep mountain terrain using only stone tools and empirical knowledge. Many canals still function today. Researchers measuring Inca hydraulic systems discovered slope variations often remained within highly controlled ranges, preventing both erosion and overflow during seasonal rainfall. At certain ceremonial sectors, water appears to have been intentionally redirected for visual and ritual effects. Flowing water in Inca cosmology symbolized life, divine order, and communication with sacred landscapes. Choqquequirao may therefore have functioned partly as a hydraulic ritual center hidden in the Andes. Some historians believe Choqquequirao was more than a religious city. Its extreme isolation gave it strategic value during the Spanish conquest. The surrounding canyon system acts almost like a natural fortress. Narrow access routes could be defended easily, while visibility across the valleys allowed long-distance observation of approaching enemies. Several researchers suspect Choqquequirao may have served as a refuge or secondary administrative center connected to the final Inca resistance at Vilcabamba. But this theory creates another mystery. The scale of engineering exceeds what would normally be required for a temporary refuge. Entire agricultural systems, ceremonial sectors, storage areas, and residential districts indicate long-term planning on a massive scale. This raises the possibility that Choqquequirao held political, religious, military, and astronomical importance simultaneously. And if over half the city still remains buried beneath jungle growth, the most important structures may not even have been discovered yet. Do you think the Inca truly understood engineering principles far beyond their time, or are we still missing a crucial piece of the Choqquequirao mystery? Share your thoughts and theories in the comments below. Perched on a steep hill above the earthquake zones of western Sumatra, Bawamataluo village has survived centuries of tropical storms, humidity, termites, and some of the strongest seismic activity on Earth. Modern engineers still debate how a pre-industrial island society built structures that behave like earthquake-resistant architecture centuries before modern structural science existed. Dutch colonial researchers documented Bawamataluo in the late 19th century, but large-scale anthropological and architectural studies only accelerated during the 20th century after scholars realized the village preserved one of the last surviving megalithic living cultures in Indonesia. After major earthquakes struck Sumatra in 2004 and 2005, engineers became even more interested because many traditional Nias houses survived surprisingly well compared to newer concrete buildings nearby. The most shocking mystery surrounding Bawah Mataluo is not the stone monuments, it is the houses. The traditional Omohada structures look ancient and fragile from the outside, yet many have survived repeated seismic events in one of the most tectonically dangerous regions on Earth. Sumatra lies near the Sunda megathrust, where the Indo-Australian plate pushes beneath the Eurasian plate. Some earthquakes in this region have exceeded magnitude 8.0. Modern seismic engineers studying Nias architecture discovered something astonishing. The houses do not behave like rigid buildings, they behave like flexible shock absorbers. Instead of fixed joints or heavy masonry walls, the structures rely on massive hardwood beams connected through interlocking wooden joints. During earthquakes, the buildings sway slightly rather than resisting movement directly. That flexibility dissipates seismic energy in ways surprisingly similar to modern base isolation systems used in skyscrapers and Japanese earthquake-resistant towers. Some support pillars are not buried deeply into the ground. Instead, they rest on carefully placed stones, reducing direct vibration transfer from the earth into the structure. This design also minimizes moisture damage in the tropical climate. Comparisons with modern reinforced concrete buildings in Indonesia after the 2005 Nias earthquake revealed a disturbing pattern. Many poorly reinforced concrete structures collapsed catastrophically, while some traditional wooden houses remained standing. Engineers noted that lighter structural mass combined with controlled flexibility may have given the ancient designs a major survival advantage. The geometry itself remains difficult to explain. The houses use sharply angled support systems beneath the floors, creating triangular load paths that distribute weight efficiently across the frame. In modern structural engineering, triangles are among the most stable load-bearing shapes. Yet the Nias builders developed these principles through observation and tradition, rather than mathematics or formal engineering science. Bawah Mataluo is filled with enormous stone chairs, ceremonial platforms, stairways, and monoliths weighing several tons. Some individual megaliths may weigh over 10 tons. The mystery is not simply how they were carved, the mystery is how they were moved uphill. The village stands more than 300 meters above sea level on elevated terrain. Nearby stone sources are not directly adjacent to the settlement. Transporting multi-ton stones through steep tropical landscapes without industrial machinery would have required extraordinary coordination. Researchers believe hundreds of workers may have used log rollers, ropes made from forest fibers, and synchronized pulling systems. But there are major problems with this explanation. Tropical rainfall makes slopes dangerously unstable. Friction alone would have made uphill movement extremely difficult. Some archaeologists compare the challenge to the transport problems seen at sites like Stonehenge or Nanma Dole. However, Bawah Mataluo's environment may have been even harder because of intense humidity, mud, and steep terrain. Several stones also display unusually flat surfaces and balanced proportions. Although iron tools existed in parts of Indonesia, achieving such shaping precision with limited metallurgy remains a serious technical question. Some contact surfaces between stones are remarkably stable even after centuries of erosion and seismic activity. This may be the greatest mystery of all. In most tropical regions, exposed wood decays rapidly. Heat, humidity, fungi, termites, and insects normally destroy untreated timber within decades. Yet some wooden components in Bawah Mataluo have survived for more than a century, and certain structural traditions may extend back far longer. For conservation scientists, this survival borders on the unbelievable. The first explanation involves material selection. The Nias people used extremely dense tropical hardwoods, including species comparable to ironwood. Some of these woods are naturally resistant to insects because of their chemical composition and density, but material alone cannot fully explain the preservation. Researchers discovered another factor hidden inside the houses themselves: smoke. traditional houses continuously exposed their beams and ceilings to smoke from indoor hearths over generations. The smoke slowly dried the timber and deposited protective chemical compounds into the wood fibers. Over decades, this created a natural preservation system somewhat comparable to industrial wood treatment. Laboratory analysis of smoke-preserved timber in Southeast Asia has shown reduced fungal growth and lower insect penetration compared to untreated wood. Some scientists compare the process to the preservation effects seen in medieval European smokehouses. Though the tropical conditions in Nias are far harsher, humidity creates another paradox. Tropical climates normally cause wood to expand, contract, and crack repeatedly. Yet many structural joints in Bawamataluo remained functional for decades because the builders designed them to move slightly with environmental changes. Instead of forcing rigidity, the architecture anticipated movement. Modern architects now study these flexible joinery systems for sustainable tropical construction. Ironically, some ancient Nias techniques may outperform certain modern building methods in humid environments because they adapt to climate instead of resisting it. There are also unresolved mysteries regarding forestry knowledge. Oral traditions suggest builders selected trees during specific seasons, sometimes linked to lunar cycles. Similar beliefs existed in Japan, Scandinavia, and parts of the ancient Mediterranean, where builders claimed wood harvested during certain moon phases lasted longer. Modern science remains divided on whether lunar harvesting significantly affects timber durability. Yet some experiments have shown seasonal sap content changes can influence fungal resistance and drying behavior. If the Nias builders understood these patterns empirically, they possessed an environmental knowledge system far more advanced than outsiders once believed. The scale of the timber is equally astonishing. Some support beams measure several meters long and carry immense weight without modern steel reinforcement. In earthquake zones, large unsupported spans are normally dangerous. Yet the Nias structures balance flexibility and mass in ways many researchers still struggle to model completely. Compared to many modern tropical buildings that deteriorate within decades, some Bawamataluo structures lasted across generations using only organic materials, manual craftsmanship, and inherited engineering traditions. That raises a deeply uncomfortable question. Did ancient builders sometimes understand local environmental engineering better than modern industrial construction? The massive stone staircase leading into the village appears simple at first glance, but closer examination reveals a sophisticated drainage strategy hidden within the layout. North Sumatra receives enormous rainfall annually, often exceeding 2,500 millimeters in some regions. Water erosion should have destabilized the pathway centuries ago, yet many stone sections remain surprisingly intact. Researchers notice subtle slope angles and narrow drainage channels integrated into the staircase system. Water rarely accumulates heavily across the walking surfaces because the design redirects runoff efficiently downhill. This resembles principles found in ancient Roman drainage engineering and Incan mountain pathways. But unlike those civilizations, the Nias builders developed these systems in relative isolation on a remote island environment. The engineering may have been entirely observational, refined over generations through trial, disaster, and reconstruction. Do you think the people of Bawamataluo discovered engineering secrets modern civilization has partially forgotten? Share your thoughts and theories in the comments below. Beneath quiet farmland in West Sussex, archaeologists uncovered a palace so advanced that many historians still struggle to explain how it appeared there only decades after Rome invaded Britain. Fishbourne Roman Palace was not supposed to exist on the edge of the empire, yet it contained giant geometric gardens, precision heating systems, imported marble, and mosaics that still retain colour after nearly 2,000 years. The site was discovered accidentally in 1960 during the installation of a water main near Chichester. Workers uncovered massive Roman foundations and fragments of mosaic flooring. Archaeologist Barry Cunliffe later began large-scale excavations and revealed a palace complex covering nearly 10 acres, making it the largest known Roman residence north of the Alps. What shocked researchers was not just the size, but the engineering sophistication hidden beneath the ruins. Fishbourne was constructed around 7580 CE, barely 30 years after the Roman conquest of Britain in 43 CE. That timeline alone created one of the site's greatest mysteries. Roman Britain at the time was still unstable, militarized, and only partially urbanized. Yet somehow builders created a palace with nearly 500 rooms, monumental courtyards, luxury bath suites, and highly symmetrical architecture comparable to elite villas near Rome itself. The logistics are difficult to explain even today. Historians estimate thousands of tons of stone, timber, clay tiles, marble, and decorative materials had to be transported across the English Channel and redistributed through muddy, undeveloped roads in Britannia. Some of the marble originated from the Mediterranean, including regions of modern Italy and Greece. Several mosaic stones were likely imported from Gaul. Moving those materials over such distances in the 1st century would have required an enormous supply network usually associated with imperial construction projects. This has led some researchers to believe Fishbourne may have been directly connected to Rome's political elite. One theory links the palace to Tiberius Claudius Cogidubnus, a pro-Roman local king mentioned in Roman inscriptions, but no definitive evidence proves he was the owner. Others believe the palace may have functioned as a political statement, a symbol meant to demonstrate Roman technological superiority to newly conquered Britain. The mosaics of Fishbourne remain one of the most technically mysterious features ever found in Roman Britain. Even after nearly 2 millennia in Britain's wet climate, many sections still preserve sharp geometry, strong pigmentation, and structural stability. In some rooms, individual tesserae remain aligned with astonishing precision, despite centuries of moisture exposure, soil pressure, and temperature fluctuation. Roman mosaic floors normally deteriorate rapidly in damp northern climates because water expands and contracts beneath the layers, eventually breaking the mortar and dislodging the stone cubes. Yet large sections at Fishbourne survived unusually well. Modern analysis revealed that the floors were built using multiple engineered layers: compacted gravel, lime mortar, crushed tile, and carefully leveled bedding materials designed to disperse pressure and control moisture movement. This layered technique resembles principles used in modern floating foundations and moisture-resistant flooring systems. Archaeologists discovered that some subfloor layers were extraordinarily uniform in thickness, suggesting careful surveying methods. Small deviations in floor angle could destroy large geometric patterns, yet many Fishbourne mosaics remain mathematically symmetrical over several meters. The pigments themselves raise even more questions. Red, yellow, and black tesserae retained remarkable color intensity compared to many medieval pigments that faded within centuries. Mineral analysis suggests that some colors came from iron-rich stone and specially treated glass heated at extremely high temperatures. Certain glass tesserae appear chemically stable enough to resist oxidation for almost 2,000 years. Some historians compare the preservation quality to mosaics found in Pompeii and Herculaneum, but Fishbourne presents a greater challenge because Britain's climate is vastly harsher for preservation. Southern Italy offers dry volcanic burial conditions. Southern England offers moisture, frost, salt air, and biological erosion. Yet parts of Fishbourne survived unexpectedly intact. The geometric accuracy is equally difficult to explain. Several mosaic patterns maintain near-perfect symmetry across large surfaces. Modern reconstructions suggest Roman artisans may have used advanced grid planning systems or precise measuring cords comparable to surveying methods later seen in Renaissance architecture. Some researchers even argue the craftsmanship exceeded what would normally be expected in a remote frontier province. Underneath the mosaics lay another mystery: the hypocaust heating system. This Roman technology functioned like an ancient central heating network. Hot air from furnaces circulated beneath raised floors and through hollow wall channels, warming entire sections of the palace. Fishbourne's hypocaust system was unusually sophisticated for Northern Europe. Excavations revealed carefully spaced brick pillars supporting suspended floors with remarkably consistent height. If those pillars varied too much, heat would distribute unevenly and create structural stress, yet many sections show evidence of precise engineering tolerances. Thermal studies suggest the system could maintain relatively stable indoor temperatures despite Britain's cold winters. Some engineers compare the airflow logic to modern passive heating systems. The Romans essentially created a controlled convection network nearly 2,000 years before modern HVAC systems existed. What makes this more mysterious is timing. Such advanced thermal engineering appeared in Britain extremely early in the occupation period. Fishbourne was not located in Rome, Alexandria, or Antioch. It stood on the far northwestern edge of the empire. Historians still debate how such expertise reached Britain so quickly after conquest. Fishbourne also contained enormous formal gardens arranged in geometric patterns. Archaeologists identified pathways, planting beds, fountains, and hydraulic channels through pollen analysis and excavation mapping. Some estimates suggest the gardens were among the earliest large ornamental Roman gardens discovered in Britain. The engineering behind them appears surprisingly advanced. Drainage channels controlled excess rainwater while maintaining soil moisture. Some researchers suspect shallow reflecting pools may have helped regulate temperature and humidity around central courtyards, creating localized microclimates similar to luxury Mediterranean villas. This concept appears centuries ahead of what historians traditionally associate with Roman Britain. Comparable garden engineering existed in wealthy villas near Pompeii, but Britain's colder environment required entirely different environmental adaptations. Fishbourne's designers may have modified Mediterranean hydraulic principles specifically for the British climate. By the late 3rd century, much of Fishbourne was destroyed by a massive fire. The exact cause remains unknown. Burn layers show intense heat in certain wings while other areas suffered relatively limited damage. Some archaeologists believe the destruction may have resulted from political violence or social unrest during the decline of Roman authority in Britain. Another mystery is why the palace was never fully rebuilt. A structure of such scale represented immense wealth and strategic importance. Yet after the fire, large sections were abandoned and gradually buried beneath soil. Over centuries, the palace disappeared almost completely from memory. Do you think Fishbourne Roman Palace was simply the result of lost Roman engineering knowledge? Or evidence that ancient Britain was far more technologically connected to the Mediterranean world than historians once believed? Share your thoughts and theories in the comments below. Beneath the modern city of Mangalia on the western coast of the Black Sea lie the buried remains of Calatis, an ancient Greek colony where seawalls resisted salt for over 2 millennia. Underground tunnels survived earthquakes, and harbour structures appear engineered far beyond what historians expected from a small Black Sea city. Calatis was founded around the 6th century BCE by Dorian Greeks from Heraclea Pontica. Systematic excavations began in the late 19th century, but the greatest discoveries emerged during the 20th and 21st centuries as archaeologists uncovered submerged harbour walls, underground catacombs, painted tombs, and massive defensive structures hidden beneath modern Mangalia. Sonar mapping and ground-penetrating radar later reveal that large sections of the city still remain underground and underwater. The greatest technological mystery of Calatis is its ancient coastal mortar. Even after nearly 2,000 years beside the Black Sea, an environment filled with salt, humidity, storms, and aggressive mineral corrosion, sections of the city's walls still remain standing. Modern engineers consider marine environments among the most destructive conditions for stone and concrete. Salt water penetrates microscopic pores, expands during temperature fluctuations, and slowly fractures structures from within. Even modern reinforced concrete often deteriorates after only 50 to 100 years near seawater, yet portions of Calatis survived for 20 centuries. Archaeological analysis revealed that the mortar used in some defensive walls contained lime mixed with unusually fine aggregates, traces of silica, and microscopic volcanic particles. This immediately shocked researchers because the Black Sea region lacks the abundant volcanic pozzolana used in famous Roman marine concrete. Roman ports such as Caesarea Maritima and Cosa relied heavily on volcanic ash imported from Italy to create hydraulic concrete capable of hardening underwater. But Calatis predates many of those Roman structures. This raises an extraordinary question. How did a relatively small Greek colony obtain or reproduce such advanced materials centuries earlier? Some researchers believe the builders imported volcanic materials through Black Sea trade networks stretching into Anatolia and the Aegean. Others argue the inhabitants may have discovered a local substitute using crushed ceramics, burnt clay, or ash from industrial furnaces. Laboratory studies found evidence that some mortar samples developed crystalline bonding structures similar to those seen in Roman marine concrete today. These crystals are important because they slowly strengthen the material over time instead of weakening it. Modern Portland cement usually degrades in seawater, but certain ancient mixtures chemically evolved into more durable forms after contact with salt water. This phenomenon has fascinated material scientists for years because it suggests ancient builders accidentally developed forms of self-reinforcing concrete. The precision of the wall construction adds another mystery. Several surviving blocks fit so tightly that almost no space exists between them. This reduced seawater penetration and minimized structural stress during storms. Similar techniques appear in much larger engineering projects such as the harbour systems of Alexandria or later Roman breakwaters, yet Calatis was never considered an engineering centre on that scale. Some marine archaeologists now suspect Calatis possessed specialized knowledge of coastal construction adapted specifically for the violent Black Sea environment, one of the most unpredictable bodies of water in the ancient world. Beneath Calatis lies a hidden network of underground passages and chambers that still remains poorly understood. Modern geophysical surveys identified tunnels running 4 to 8 meters below the city, many constructed with surprisingly advanced vaulted ceilings capable of distributing weight and resisting collapse. The Black Sea region experiences frequent seismic activity. Ancient underground systems typically collapse over centuries due to shifting soil and water infiltration. Yet portions of Calatis's subterranean structures remained intact long after the surface city was destroyed or rebuilt. The purpose of these tunnels remains controversial. Some archaeologists believe they served as storage chambers for grain, wine, oil, and imported goods. Underground temperatures remain relatively stable year-round, creating natural refrigeration systems centuries before mechanical cooling existed. Others argue the tunnels had ritual functions connected to mystery cults and Orphic traditions known to exist in Greek Black Sea colonies. Several chambers appear too elaborate for ordinary storage. Some contain carefully shaped stone niches, hidden corridors, and ventilation shafts that seem designed for long-term underground activity. Comparisons are often made with the underground cities of Cappadocia in Turkey, although the systems at Calatis are much smaller. Still, the engineering logic is surprisingly similar. Stable airflow, thermal insulation, hidden entrances and structural arches designed to resist seismic pressure. No definitive explanation has ever been agreed upon. Today, much of ancient Calatis lies underwater. Rising sea levels and coastal erosion gradually submerged sections of its harbour over centuries. But sonar scans beneath the Black Sea revealed something unexpected. Massive stone alignments resembling artificial breakwaters and engineered harbour platforms. Some blocks weigh several tons. More surprising is the precision of their placement. Certain sections appear interlocked in ways that minimized wave pressure and distributed force across entire walls. Modern engineers studying the site noted similarities with hydraulic harbour systems used by the Romans centuries later. This is difficult to explain because constructing maritime infrastructure in open water during the Hellenistic era was extraordinarily difficult. Ancient cranes had limited lifting capability, underwater visibility was poor, and stabilizing foundations in moving seawater required advanced planning. Yet the harbour of Calatis appears intentionally designed to manipulate wave energy. Computer simulations of Black Sea coastal currents suggest the harbour layout may have reduced direct storm impact by redirecting incoming wave force along angled stone barriers. If true, the builders understood coastal hydrodynamics at a level historians rarely associate with smaller Greek colonies. The Black Sea itself may explain why such technology developed here. Ancient sailors feared its sudden storms and violent winter waves. Greek records often describe the sea as unpredictable and deadly. A city dependent on maritime trade would have needed highly sophisticated coastal defences simply to survive. One of the most astonishing discoveries near Calatis was the painted Hypogeum tomb found near Mangalia. The underground structure contained wall paintings and pigments preserved far beyond what experts expected in a humid coastal environment. Normally, moisture destroys ancient pigments quickly. Salt crystallization causes plaster layers to crack and separate from walls. Yet red, blue and black pigments inside the tomb remained visible after more than 2,000 years underground. Microscopic analysis detected layered applications of mineral-based pigments combined with protective surface coatings. Some preservation characteristics resemble later Roman fresco technologies that supposedly became widespread centuries afterward. The tomb also featured carefully engineered humidity control. Narrow ventilation shafts appear positioned to reduce condensation while maintaining stable internal temperatures. Similar environmental engineering principles are seen in Egyptian tombs and certain Nabatean burial chambers, but their appearance in Calatis surprised researchers. The preservation was so unusual that some specialists described the chamber as a microclimate capsule designed to slow natural decay. Another overlooked mystery is the orientation of Calatis itself. Several roads and structures do not align naturally with the coastline. Instead, their angles correspond closely to specific solar positions during seasonal transitions. This has led some historians to compare Calatis with planned cities such as Alexandria or Priene, where astronomy influenced urban design. But in Calatis, the alignments may have served maritime purposes rather than purely religious ones. Researchers noticed that certain street orientations matched prevailing seasonal wind patterns across the western Black Sea. If intentional, this would suggest the city combined astronomy, navigation, and environmental engineering into a unified urban system. Such planning would have provided advantages for harbour visibility, smoke ventilation, sailing schedules, and even defensive signalling across the coast. What do you think is still hidden beneath Calatis? A lost harbour technology, underground engineering system, or evidence of knowledge far ahead of its time? Share your thoughts in the comments below. High in the mountains near Ayacucho, Peru, Huarihuilca still stands like a forgotten machine from a vanished empire. Long before the Inca rose across the Andes, the Wari were already building earthquake-resistant complexes, underground chambers, and astronomical alignments at nearly 2,700 meters above sea level. Some archaeologists now believe the Wari may have created the technological blueprint later perfected by the Inca themselves. The site was first systematically documented during 20th century archaeological surveys around the ancient Wari capital region. Excavations revealed ceremonial chambers, underground tombs, precision-cut stone walls, and urban planning unlike anything expected from an Andean civilization of the 7th to 10th centuries. Carbon dating placed major construction phases between roughly 600 and 1000 CE, during the height of the Wari Empire, centuries before Machu Picchu. What makes Huarihuilca extraordinary is not simply its age, but the engineering logic hidden inside the ruins. Nearly every structure appears designed for survival in one of the harshest geological environments on Earth. Peru sits directly along the Pacific Ring of Fire, where powerful earthquakes have repeatedly destroyed cities throughout history. Yet many Wari walls remain standing after nearly a millennium. Archaeologists discovered that some foundations were built using layered construction systems. Compacted soil, smaller stones, and larger outer blocks arranged to absorb seismic shock. Certain walls leaned slightly inward rather than standing perfectly vertical, a feature later famous in Inca architecture at Cusco and Sacsayhuaman. Modern structural engineers recognize this inward tilt as an effective way to reduce collapse during lateral ground movement. The mystery is timing. The Wari developed these techniques centuries before the Inca Empire reached its peak. Unlike Rome or China, they had no iron tools, no wheeled transport system for construction, and no draft animals capable of pulling multi-ton stones uphill. Yet they produced stone complexes capable of resisting seismic activity for nearly 1,000 years. Some researchers compare the Wari approach to primitive forms of dynamic load distribution, a concept used in modern earthquake engineering. Even more fascinating is the possibility that this knowledge came not from mathematics, but from centuries of direct observation and experimental reconstruction after repeated earthquakes. In other words, the Wari may have evolved engineering through long-term disaster adaptation. The stonework itself presents another puzzle. While not as perfectly interlocked as later Inca masonry, many blocks were shaped with surprising precision. Certain joints are so tight that inserting a knife blade between stones becomes difficult even today. Tool marks suggest abrasion techniques using harder minerals and sand slurry rather than metal chisels alone. Similar methods were used in parts of ancient Egypt, particularly during the shaping of granite blocks at Giza. Under several structures lies a network of narrow underground chambers connected by hidden passageways. Many are too confined for ordinary storage or habitation. Ventilation shafts appear intentionally placed to regulate airflow, and some chambers maintain remarkably stable temperatures compared to the extreme thermal swings outside. At high elevations in the Andes, daytime and nighttime temperatures can differ by over 20 degrees Celsius. Yet certain underground spaces remain comparatively stable year-round. Researchers believe the Wari may have exploited thermal inertia within stone and soil to create passive climate-controlled environments, an ancient form of environmental engineering. The exact purpose of these chambers remains debated. Some archaeologists interpret them as elite burial spaces, while others believe they served ceremonial functions connected to ancestor worship or altered states of consciousness. Acoustic testing inside similar Wari ceremonial structures has shown that narrow stone corridors can amplify echoes and distort voices in unsettling ways. This raises the possibility that ritual specialists deliberately used architecture to create psychological effects during ceremonies. Human remains discovered within the complex deepen the mystery further. Several burials showed remarkable preservation despite their age. Hair, woven textiles, and traces of skin survived in some cases for centuries. While the dry Andean climate played a role, researchers suspect the chamber placement itself may have been engineered to reduce humidity and maximize airflow. Textiles recovered from Wari sites across Peru demonstrate astonishing technical sophistication. Some fabrics contain thread counts exceeding 250 threads per inch, comparable to certain high-end modern textiles and finer than many medieval European fabrics produced centuries later. Dyes derived from minerals and plants remained vivid after nearly 1,000 years, suggesting advanced chemical understanding of pigments and fiber treatment. The Wari were not isolated builders. They controlled one of the earliest large-scale imperial systems in South America, stretching across vast portions of Peru through roads, administrative centers, and agricultural networks. Before the Inca road system ever connected the Andes, the Wari had already established routes through mountains, deserts, and valleys. Some roads associated with Wari expansion reveal multi-layered foundations engineered to resist seasonal erosion. Drainage channels diverted rainwater away from pathways, while retaining walls stabilized steep slopes. Comparisons with Roman roads are unavoidable. Both civilizations built infrastructure not merely for movement, but for long-term imperial control. Yet the greatest mystery surrounding Wari Wilcawain may not lie underground or within its walls. It may lie in the sky. Several structures appear aligned with the solar events, particularly solstices and equinoxes. Narrow openings allow sunlight to strike specific interior locations during precise moments of the year. In some chambers, sunlight enters only briefly, illuminating ritual spaces with almost unnatural accuracy. Archaeoastronomers studying Andean civilizations note that tracking the sun at high altitudes is both easier and more difficult than many assume. The thin atmosphere creates sharper solar visibility, but mountainous terrain complicates horizon calculations. To create reliable alignments, observers would likely need decades, possibly generations, of repeated measurements. At Wari Wilcawain, some alignments suggest intentional synchronization between architecture and seasonal cycles critical for agriculture, ritual calendars, and political authority. In the Andes, controlling knowledge of celestial timing meant controlling planting seasons, water management, and ceremonial legitimacy. The most controversial theory proposes that Wari priests used these solar events as engineered religious experiences. Imagine entering a dark underground chamber after hours of ritual preparation. Suddenly, for only a few minutes on a specific day each year, a beam of sunlight cuts through total darkness and illuminates a sacred object or burial chamber with impossible precision. To ancient observers, such an event would not appear scientific, it would appear divine. Similar effects existed in other ancient civilizations. At Abu Simbel in Egypt, sunlight penetrates the temple interior during specific days associated with Ramses II. At Newgrange in Ireland, winter solstice light enters a narrow passage built over 5,000 years ago. Chichen Itza in Mexico creates the illusion of a descending serpent during equinox sunsets. But Wari Wilcawain stands apart because far less is known about the civilization that built it. Unlike Egypt or Rome, the Wari left behind no extensive written records explaining their knowledge systems. Their astronomical understanding survives only through stone orientation, architectural geometry, and the shadows still moving silently across the ruins. Some researchers believe later Inca astronomy may have inherited Wari foundations. Others argue the Wari developed entirely independent systems, later absorbed into broader Andean traditions. The problem is evidence. Much of Wari intellectual history disappeared during political collapse around the 11th century. What do you think truly caused the collapse of the Wari civilization? Climate disaster, internal conflict, or the loss of knowledge over time? Share your theory in the comments below. Beneath the quiet hills of Gloucestershire, England, Chedworth Roman Villa preserves evidence of technologies so advanced that some engineers believe parts of the villa were centuries ahead of their time. Beneath collapsed stone floors lie heating systems, waterproof materials, and mosaics whose colours survived nearly 2,000 years of moisture, frost, and darkness in one of the wettest climates of Roman Britain. The villa was accidentally discovered in 1864 after a gamekeeper noticed fragments of mosaic emerging from the ground near a rabbit hole. Excavations soon revealed one of the largest and most technologically sophisticated Roman villas ever found in Britain, covering more than 500 square metres with the bath complexes, hypocaust heating systems, water channels, and elaborate decorated rooms. But the deeper archaeologists dug, the stranger the site became. The greatest mystery of Chedworth is not its walls or baths, it is the mosaics. Many of the villa's floors still contain geometric and floral mosaics whose colours remain surprisingly vivid after nearly 2 millennia underground. In some rooms, reds, blacks, creams, and terracotta shades remain sharply visible despite Britain's constant humidity, acidic soil, winter frost cycles, and centuries of groundwater exposure. Modern conservators consider this survival extraordinary because most Roman mosaics exposed to repeated moisture eventually suffer mineral salt crystallization, pigment decay, biological growth, or surface fragmentation. Yet parts of Chedworth survived conditions that should have destroyed them centuries ago. Researchers discovered that the tesserae, the tiny mosaic cubes, were cut from unusually dense limestone and iron-rich stone capable of resisting water penetration better than softer local materials. Some black tesserae contain high concentrations of carbon-rich minerals that oxidize extremely slowly, helping preserve their color stability. But the real mystery lies beneath the surface. Microscopic analysis revealed traces of an unusually compact mortar layer underneath several mosaic sections. The mortar appears to contain lime mixed with crushed ceramic particles and silicate-rich aggregates. This mixture resembles pozzolanic concrete used in Roman harbours and marine structures around the Mediterranean. That comparison shocked researchers because Chedworth lies nearly 1,500 kilometres from the volcanic regions normally associated with Roman pozzolana technology. Yet the villa's builders somehow produced flooring layers with remarkable resistance to moisture expansion and thermal cracking. Some archaeologists believe Roman engineers in Britain may have adapted Mediterranean formulas using locally available minerals, while others argue the builders possessed practical chemical knowledge far more advanced than historians once assumed. Even more mysterious is how the mosaics interacted with light. Several rooms appear intentionally designed so morning or afternoon sunlight would strike the tesserae at low angles, causing reflective minerals inside the stone to intensify contrast patterns. Certain geometric motifs become dramatically clearer under angled illumination, almost like optical engineering embedded into the floor itself. Modern digital imaging has shown that some mosaic layouts also exhibit near-perfect symmetry over large surfaces despite being assembled manually. In certain sections, alignment deviation is less than a few millimeters across multiple meters of flooring. For comparison, many medieval European floors constructed more than 700 years later show significantly less precision. The question is unavoidable. How did craftsmen working in remote Roman Britain achieve decorative engineering capable of surviving nearly 2,000 years of environmental destruction? Beneath the villa lies another technological anomaly, a hypocaust heating network so advanced that historians compare it to early central heating. The system functioned by elevating floors on hundreds of small brick pillars called pili stacks. Hot air generated by furnaces flowed beneath the suspended floors before rising through hollow wall flues to heat entire rooms evenly. At Chedworth, archaeologists found evidence of multiple heated rooms operating simultaneously, including baths, living chambers, and reception halls. What makes this extraordinary is the location. Roman Britain was cold, wet, and located at the extreme northern frontier of the empire. Maintaining hypocaust systems required enormous fuel consumption, constant maintenance, and sophisticated airflow control. Yet thermal modelling suggests some rooms at Chedworth could retain warmth for hours after furnaces stopped burning. Researchers studying surviving flue layouts discovered remarkably efficient heat circulation patterns. Certain channels narrow strategically to increase airflow velocity, while thicker flooring layers above heated sections helped retain thermal energy. Some engineers compare the design to modern radiant floor heating systems. Even the bricks themselves remain puzzling. Several hypocaust components show signs of firing temperatures exceeding 900 degrees Celsius, unusually high for provincial Roman Britain. These bricks survived repeated heating and cooling cycles that normally fracture ancient ceramics over time. Some materials scientists believe Roman kiln control techniques may have been far more precise than previously estimated. Another unexplained feature is the villa's mortar. Despite nearly 2 millennia of rain exposure, many structural sections remain chemically stable. Researchers examining microscopic fractures discovered traces of secondary calcite crystals forming inside cracks. This phenomenon resembles self-healing reactions observed in Roman marine concrete. When water penetrates tiny fractures, dissolved lime particles can recrystallize and partially reseal the damaged area. Modern experimental concretes attempt to reproduce similar behavior, yet Roman builders achieved it without industrial chemistry. Comparisons with modern Portland cement are revealing. Many modern concretes begin significant chemical degradation within decades under constant moisture exposure. Yet portions of Chedworth's mortar survived almost 2,000 years in Britain's aggressive freeze-thaw climate. Some scientists suspect Roman builders deliberately engineered mineral reactions they did not fully understand scientifically, but mastered through generations of empirical experimentation. The villa was carefully positioned near natural springs, allowing Roman engineers to construct an integrated water management network. Stone-lined channels transported water through baths, storage tanks, and drainage systems using only gravity. Laser surveys conducted during modern archaeological mapping revealed astonishingly precise gradients. Some channels maintained slopes accurate enough to sustain smooth water flow over long distances without erosion or stagnation. That level of hydraulic precision normally appears in major Roman aqueducts, not rural villas hidden in the English countryside. Waterproof coatings inside certain tanks also remain surprisingly intact. Chemical analysis suggests builders used layered lime compounds combined with crushed ceramics to create highly durable hydraulic surfaces. The same principle appears in Roman ports across the Mediterranean. Again, the mystery is technological transfer. How did frontier engineers in distant Britannia replicate methods used in Rome's greatest imperial infrastructure? Do you think the Romans truly understood advanced climate engineering? Or were these technologies discoveries that humanity later lost for centuries? Share your thoughts in the comments below. Potaissa in modern-day Transylvania, Romania, once housed more than 5,000 soldiers of Legio Macedonica. What archaeologists uncovered there was not just another Roman frontier settlement, but evidence of engineering systems, metallurgy, an industrial organization that still raise questions today. Potaissa was first systematically identified in the 19th century near the city of Turda, after Roman inscriptions, military bricks, and buried road networks began emerging from the soil. Large-scale excavations later revealed baths, military barracks, workshops, water systems, and an enormous legionary fortress covering nearly 23 hectares. But the deeper researchers dug, the stranger the technology appeared. Potaissa existed in one of the coldest regions occupied by the Roman Empire. Winter temperatures in Transylvania frequently dropped below -15 degrees Celsius, yet the city maintained massive heated bath complexes and warm military quarters nearly 1,800 years ago. Archaeologists discovered advanced hypercore systems beneath floors and inside walls. Hot air generated by furnaces circulated through hollow chambers under stone floors, creating radiant heating remarkably similar to modern underfloor systems. While hypocausts existed elsewhere in the Roman world, the systems at Potaissa appear unusually optimized for harsh climates. Some bricks excavated from the heating chambers show thermal damage indicating repeated exposure to temperatures above 900 degrees Celsius. That alone is puzzling. Maintaining such stable temperatures with ancient wood-fired furnaces would have required highly controlled airflow and specialized refractory materials. Researchers comparing the bricks to those from Pompeii found differences in mineral composition. Unlike Italian Roman cities that benefited from volcanic pozzolana ash, Transylvania lacked nearby volcanic resources. Yet many Potaissa bricks display similar resistance to thermal cracking. This has led some materials scientists to suspect the Romans developed a lost regional formula involving silica-rich sands or imported mineral additives. Even more surprising is the efficiency of the airflow layout. Several reconstructed models suggest the heating system minimized fuel waste in ways comparable to 19th century industrial furnace engineering. For a military settlement on the edge of the empire, the sophistication is difficult to explain. The military roads connecting Potaissa to Apulum and Napoca remained partially intact after nearly 2 millennia of erosion, freeze-thaw cycles, and seismic activity. At first glance, they appear like ordinary Roman roads, but geological analysis revealed something far more advanced beneath the surface. Engineers layered the roads with multiple structural zones: large stones below for load distribution, compact gravel in the middle to absorb vibration, and tightly compressed crushed stone above for drainage and durability. Some road sections maintain a slope gradient so precise that water still naturally drains off the surface today. Modern surveys found deviations in angle surprisingly small, considering the roads were built without laser instruments, modern surveying equipment, or powered machinery. What truly confuses historians is the consistency across mountainous terrain. Maintaining uniform grades through hills and valleys would have required extraordinary planning and measurement techniques. Roman surveyors used tools like the groma and chorobates, but many experts argue those alone cannot fully explain the precision achieved across such distances. Comparisons with later medieval roads in the same region make the contrast even stranger. Many roads built more than 1,000 years later deteriorated faster than the Roman originals beneath them. The greatest mystery of Potaissa may not be its architecture, but its metallurgy. Legio V Macedonica was stationed there for nearly 170 years, meaning the fortress operated as a giant military-industrial centre, producing weapons, armour, tools, nails, fittings and machinery components on a massive scale. Excavations uncovered slag deposits, furnaces, iron fragments, unfinished blades, and workshop zones indicating continuous metal production. But microscopic analysis of several iron objects revealed patterns that should have been extremely difficult to achieve with Roman-era technology. Some blades discovered at Potaissa contain uneven carbon distribution remarkably similar to differential hardening techniques used in later medieval and even Japanese sword-making traditions. The edges appear harder than the core, allowing weapons to remain sharp without becoming brittle. This is significant because controlled carbon diffusion requires careful temperature regulation during forging. If overheated, the metal weakens. If cooled too quickly, it cracks. Yet several analyzed samples display evidence of highly controlled thermal treatment. Researchers examining the microstructure found traces of martensitic transformation in portions of certain blades, a hardened crystal structure formed through rapid cooling. In modern metallurgy, this process requires precise quenching conditions. Water cooling alone often causes fractures, especially in larger blades. Some scientists now suspect Roman smiths at Potaissa may have experimented with oil quenching or organic cooling mixtures. Residue traces found near workshop areas include carbonized fats and plant oils, though definitive proof remains elusive. The furnaces themselves are equally mysterious. Reconstructed airflow models suggest some workshop furnaces may have reached temperatures exceeding 1,200 degrees Celsius, approaching conditions needed for advanced bloomery steel refinement. Achieving this consistently would require extremely efficient bellows systems and sophisticated control of oxygen flow. Even more intriguing is the scale of production. Thousands of stamped bricks marked Leg V Mac suggest the Legion operated almost like a state-controlled industrial corporation. Roman soldiers were not merely fighters. They functioned as engineers, blacksmiths, builders, logisticians, and industrial labourers simultaneously. Compared to many medieval European workshops centuries later, Potaissa's production system appears astonishingly organised. Supplying water to an elevated Roman fortress in rugged terrain should have been extraordinarily difficult. Yet Potaissa maintained baths, fountains, drainage systems, and storage reservoirs with remarkable consistency. Archaeologists uncovered ceramic and lead pipes designed to handle stable water flow over long distances. Some pipe joints remain sealed after nearly 2,000 years. The biggest mystery involves pressure management. Certain bath structures sat at elevations requiring carefully calculated hydraulic gradients. To maintain continuous flow, Roman engineers likely used primitive pressure-balancing reservoirs or elevated storage towers. What makes this difficult to explain is the level of precision required. A slight miscalculation in slope would either stop the flow entirely or rupture weaker sections of pipe. Hydraulic engineers comparing the system to later medieval infrastructure found Roman design significantly more stable in some cases. It raises an uncomfortable question. Did Roman frontier engineers possess practical hydraulic knowledge that Europe later lost for centuries? One of the strangest discoveries at Potaissa involves standardization. Thousands of bricks stamped with the insignia of Legio V Macedonica were manufactured with dimensions so consistent they resemble machine-produced materials. Roof tiles, pipes, floor components, and structural bricks followed highly uniform measurements across the entire fortress. This level of standardization dramatically simplified repairs, military expansion, and logistics. Modern industrial systems rely on interchangeable parts for the same reason. Researchers estimate that constructing and maintaining the fortress required moving tens of thousands of tons of stone, timber, clay, and metal through mountainous terrain. Without engines, electricity, or mechanized transport, the organizational complexity becomes staggering. Some historians argue the Roman military functioned less like an ancient army and more like a mobile engineering civilization. Do you think Potaissa proves that entire technologies can disappear from history within just a few generations? Share your thoughts in the comments below. Aerial scans over Europe kept revealing the same strange pattern. Massive rectangular fortresses buried beneath forests, deserts, and farmland from Britain to Syria. These were Roman castrums, military camps supposedly built in days by marching legions nearly 2,000 years ago. Yet modern excavations uncovered engineering precision that seems impossible for temporary structures. Near modern-day Germany, archaeologists found drainage channels still carrying rainwater after centuries underground. In Romania, buried roads connected to fortress gates with near-perfect geometric alignment. In northern England, fort foundations survived repeated freeze-thaw cycles that destroyed later medieval structures nearby. The deeper researchers excavated, the stranger the technology appeared. Roman castrums were never meant to last forever. Historical texts describe them as rapidly constructed military compounds designed for expansion, defense, and troop movement. Yet many surviving ruins display a level of engineering more comparable to planned modern infrastructure than ancient emergency camps. The mystery is not simply how the Romans built them, but how they repeated the same precision across 3 continents without engines, digital mapping, or industrial machinery. One of the first unexplained mysteries is geometric standardization. Archaeologists studying castrums from Spain to the Middle East discovered that many followed nearly identical layouts regardless of terrain. The main roads, called the Cardo and Decumanus, intersected at almost exact right angles. Gates aligned symmetrically with internal buildings. Barracks, granaries, baths, and defensive walls often followed mathematical ratios repeated across thousands of kilometers. What makes this extraordinary is the scale. The Roman Empire stretched over roughly 5 million square kilometers at its peak, yet frontier forts separated by deserts, mountains, and seas still show near-identical engineering logic. Modern laser surveys at several sites revealed alignment errors sometimes smaller than a fraction of a degree. Even some modern construction projects struggle to maintain such consistency without advanced surveying equipment. The Romans supposedly relied on tools like the groma, a simple wooden surveying instrument using weighted cords, but many engineers argue these tools alone cannot fully explain the observed precision. Some researchers believe Roman military surveyors possessed advanced practical mathematics lost after the collapse of the empire. Others suspect they used astronomical positioning methods far more sophisticated than surviving Roman manuals describe. Compared to medieval fortifications, the difference becomes dramatic. Medieval castles often evolved chaotically over centuries depending on terrain and war demands. Roman castrums, however, resemble modular blueprints copied with almost industrial consistency. Satellite imagery has even uncovered buried fort outlines invisible from the ground, revealing hidden geometric systems beneath modern cities and farmland. Another major mystery involves Roman concrete and construction materials. Excavations at several castrum ruins uncovered foundations still structurally stable after nearly 2 millennia of earthquakes, frost, erosion, and warfare. Modern concrete often begins degrading within 50 to 100 years due to cracking, moisture infiltration, and chemical decay. Yet some Roman military foundations appear stronger today than when first constructed. Scientists analyzing Roman mortar discovered microscopic mineral crystals called aluminous tobermorite forming inside the material over time. These crystals slowly reinforce the structure through chemical reactions involving volcanic ash, lime, and moisture. In effect, parts of Roman concrete may heal themselves naturally. What confuses researchers is that this technology appears across distant military regions, including areas far from Italy's volcanic zones. Some frontier forts in Britain and Central Europe used mixtures with remarkable resistance to water and temperature changes despite lacking easy access to volcanic materials. This suggests Roman engineers either transported specialized ingredients over enormous distances or possessed regional formulas adapted to local geology. At some excavated sites, buried walls survived better than nearby medieval churches built more than 1,000 years later. In parts of Germany, Roman drainage foundations remain more stable than modern concrete repairs added during the 20th century. Engineers studying these ruins have openly admitted that certain long-term chemical processes inside Roman concrete are still not fully replicated by modern industry. Water management inside Roman castrums creates another engineering puzzle. Many ruins contain underground drainage systems with gradients so accurate that water still flows properly after excavation. Laser measurements in several forts revealed slope variations measured only in millimeters across long distances. That level of hydraulic precision becomes even more astonishing considering the terrain. Roman forts were often constructed on muddy plains, rocky hills, or unstable frontiers vulnerable to flooding. Yet the Romans consistently created underground channels capable of controlling runoff, sewage, and groundwater without pumps or powered machinery. Some castrums also included heated bath complexes using hypercore systems, networks of hollow floors and walls circulating hot air beneath rooms. These systems acted almost like primitive central heating. In colder regions such as Britain, archaeologists discovered evidence that some drainage and heating systems were adapted specifically to freezing climates. Comparisons with later European infrastructure raise uncomfortable questions. In some regions, medieval settlements abandoned Roman drainage networks because they no longer understood how to maintain them. Several ancient Roman roads and channels remained functional long after surrounding post-Roman infrastructure collapsed. The roads connecting these castrums may be even more mysterious than the forts themselves. Roman military highways crossed mountains, marshes, rivers, forests, and deserts with astonishing efficiency. Many were built using multiple structural layers: compacted earth, crushed stone, gravel, and elevated drainage surfaces. Some roads still survive today beneath modern highways because engineers discovered the Roman routes remained the most stable paths through difficult terrain. Archaeological evidence suggests Roman legions could march roughly 25 to 30 kilometers per day while carrying heavy equipment. Maintaining this logistical speed across thousands of kilometers required supply coordination on a scale that seems almost impossible for the ancient world. Certain frontier forts appear positioned at mathematically optimized intervals for signaling and reinforcement. Beacon towers allowed communication across long distances. Some researchers compare the Roman military network to an ancient analog version of modern logistical infrastructure. The mystery deepens when considering construction speed. Ancient writers claimed Roman soldiers could build fortified camps overnight during campaigns. That included trenches, wooden defences, watchtowers, roads, command structures, and organised internal layouts. Modern military engineers estimate that constructing comparable fortified compounds today would normally require mechanised excavation equipment and large logistical support systems. Even more puzzling is how much of this knowledge disappeared after the fall of Rome. Following the collapse of the Western Roman Empire in the 5th century, Europe entered centuries where large-scale infrastructure quality sharply declined. Roads deteriorated, urban sanitation weakened. Massive stone engineering became rarer. In many regions, people literally dismantled Roman structures because reproducing them from scratch was too difficult or expensive. Some historians believe Roman engineering superiority came from centuries of accumulated experimentation inside the military. Legion engineers constantly adapted techniques for local climates, materials, and terrain. Others argue significant technical manuals and mathematical systems were permanently lost during the destruction of Roman libraries and administrative centres. The most controversial theories suggest Roman engineering may have been more advanced than surviving historical texts imply. Practical knowledge passed directly through military training may never have been fully documented. Certain construction techniques visible in castrum ruins were not equalled again until the Industrial Age. Do you think the Romans truly possessed lost engineering knowledge far ahead of their time? Or are modern historians still underestimating ancient technology? Share your thoughts in the comments below. Housesteads. Roman fort sits along the most dramatic section of Hadrian's Wall in northern England, nearly 300 metres above sea level on the basalt cliffs of the Windshill Escarpment. The fort was officially excavated in the early 1800s, but major archaeological investigations accelerated during the late 19th and 20th centuries when researchers uncovered barracks, hospitals, granaries, heating systems, drainage channels, and one of the best preserved Roman military latrines ever found. What shocked archaeologists was not simply the survival of the structures, but the level of engineering sophistication hidden inside a fortress built almost 1,900 years ago in one of the coldest and wettest frontiers of the Roman Empire. Unlike Mediterranean Roman cities protected by stable climates, housesteads endured freezing winters, violent Atlantic winds, acidic rainwater, and repeated frost expansion. Yet many of its drainage systems, stone foundations, and thermal structures still function better than some medieval constructions built over 1,000 years later. That contradiction became the beginning of one of Britain's greatest ancient engineering mysteries. Modern engineers describe the Windshill Ridge as an extremely difficult construction environment. The volcanic basalt beneath housesteads is incredibly hard but fractured by ancient geological stress. Combined with freeze-thaw cycles, the terrain constantly shifts microscopically over time. Normally, rigid masonry built on such terrain develops major cracks after centuries of thermal expansion. Yet many wall sections at housesteads remain remarkably stable. Excavations revealed that Roman engineers avoided creating completely rigid foundations. Instead, they layered stones of different sizes beneath major walls, allowing pressure and movement to disperse naturally through the structure. This resembles modern stress distribution engineering used in earthquake-resistant construction. What makes the mystery deeper is the precision involved. Some retaining walls were aligned at angles specifically designed to redirect rainwater runoff away from load-bearing sections. Researchers studying erosion patterns discovered that several drainage slopes differ by only a few degrees, suggesting Roman surveyors had advanced topographical measurement skills despite lacking modern instruments. Compared to medieval castles built in Britain more than 1,000 years later, housesteads shows far superior long-term water management. Many Norman fortifications suffered major foundational collapse within centuries, while sections of housesteads still stand after nearly 2 millennia. One of the most astonishing discoveries at housesteads was its communal latrine system. At first glance, it appears simple, rows of stone seats positioned above flowing water channels. But modern hydraulic engineers became fascinated when they realized how advanced the design actually was. The fort sat high above nearby water sources, yet Roman engineers created a gravity-fed system capable of continuously flushing waste downhill without mechanical pumps. Water entered through carefully calculated channels and maintained enough velocity to prevent sediment buildup while avoiding destructive turbulence. This is where the mystery begins. Northern England contains hard water rich in dissolved minerals, especially calcium carbonate. Over centuries, mineral deposits normally clog narrow drainage systems, but large portions of the housestead's channels remained operational for extraordinarily long periods. Some researchers believe Roman engineers understood flow dynamics far better than previously assumed. The channels appear slightly curved in critical sections, reducing stagnation zones where mineral accumulation normally occurs. Several drainage stones were also polished unusually smooth, decreasing friction and improving water velocity. The placement of the latrine itself adds another mystery. It was constructed near one of the windiest edges of the fort. Modern airflow simulations suggest the location naturally created a ventilation effect that continuously pulled odours away from occupied areas. In other words, the Romans may have unintentionally, or intentionally, created a passive air extraction system centuries before modern sanitation engineering. Even more surprising, traces of antibacterial minerals have been identified in some drainage sediments, raising questions about whether certain stone materials were deliberately selected to reduce contamination. Housesteads existed near the northern edge of the Roman world, where winter temperatures could regularly drop below freezing. Yet excavations uncovered evidence of heated baths, warm living quarters, and underfloor heating systems known as hypercausts. The Romans built hollow spaces beneath floors supported by stone pillars. Furnaces pushed hot air beneath the rooms and through hollow wall channels, effectively turning entire buildings into giant radiators. But archaeologists encountered several anomalies. The fuel consumption estimates do not fully match the thermal performance implied by the surviving structures. According to some reconstructions, maintaining consistent temperatures in such extreme conditions should have required enormous quantities of wood every day. Yet carbon residue inside some heating channels appears surprisingly low. This has led to multiple theories. Some researchers believe Roman engineers optimized airflow using pressure differentials created by the fort's elevation and prevailing winds. Others suspect the buildings were insulated more effectively than previously thought, possibly through layered plaster mixtures containing lime and volcanic additives. Thermal modelling conducted on reconstructed Roman bath systems has shown efficiency levels far higher than expected for ancient technology. In certain conditions, the hypercaust design distributed heat more evenly than some early industrial-era heating systems from the 18th century. Another mystery involves moisture control. Heated rooms normally create condensation damage in cold climates, especially in stone buildings. Yet portions of housesteads display far less internal erosion than expected. This suggests the Romans may have mastered passive humidity regulation techniques that are still poorly understood. Housesteads was not isolated. It functioned as one node in a defensive network stretching roughly 117 kilometers across northern Britain. What fascinates historians is the precision with which Roman forts and watchtowers were positioned. Many maintain direct lines of sight across enormous distances, despite difficult terrain filled with hills, valleys, and cliffs. Modern visibility studies using digital terrain mapping suggest signals from housesteads could potentially travel across multiple forts within minutes using fire or reflective devices. That level of coordination would have allowed Roman commanders to move information faster than many medieval kingdoms centuries later. The real puzzle is how Roman surveyors achieved such accuracy. Without satellites, aerial mapping, or laser equipment, Roman engineers somehow calculated optimal sight lines across vast landscapes. Small alignment errors would have broken the communication chain entirely. Yet the system functioned across one of Britain's harshest regions. Some archaeologists argue Roman military surveyors possessed highly advanced geometric methods, now poorly documented in surviving texts. Others believe they developed practical observational techniques through generations of military engineering experience, lost after the collapse of the empire. The network's efficiency becomes even more impressive when compared with later medieval warning systems, many of which suffered severe visibility failures due to inaccurate placement. A permanent garrison of hundreds of soldiers required enormous quantities of fresh water every day for drinking, cooking, cleaning, bathing, and sanitation. Maintaining such a supply atop a rocky ridge appears almost impossible. Yet housesteads survived for centuries. Archaeologists discovered sophisticated rainwater collection systems connected to reservoirs and stone-lined channels. Tiny gradient adjustments directed runoff into storage basins while minimizing erosion. Some gradients differ by less than 2 degrees, requiring remarkable surveying precision. More mysterious still are traces of waterproof mortar coatings found inside certain reservoirs. Chemical analysis revealed mixtures of lime, crushed ceramics, and mineral additives similar to hydraulic concretes used in Roman harbours around the Mediterranean. That discovery shocked researchers because such advanced waterproofing technologies were not expected at a remote frontier outpost thousands of kilometres from Rome itself. Comparisons with many medieval British forts reveal a dramatic difference. Numerous later castles struggled with contaminated or seasonal water supplies, while housesteads maintained a relatively stable hydraulic infrastructure under far harsher conditions. Wall of Romulus was uncovered through excavations around Rome's Palatine Hill, the legendary birthplace of the city itself. Archaeologists investigating layers beneath later Roman structures found sections of massive volcanic stone fortifications dating back to the 8th century BCE, the same era traditionally linked to Romulus. What shocked researchers was not only the age of the wall, but the sophistication hidden inside it. The structure appeared far too advanced for what historians once believed was merely a small tribal settlement beside the Tiber River. The surviving remains suggest an organized defensive barrier built with carefully fitted blocks of volcanic tuff, some weighing several hundred kilograms each. Carbon dating from surrounding organic material and ceramic fragments placed portions of the construction around 730–720 BCE. That timeline places the engineering of the wall centuries before Rome became a dominant Mediterranean power. Compared to many early Italic settlements of the same period, the Wall of Romulus appears unusually strategic, unusually durable, and unusually precise. What began as a routine excavation quickly evolved into one of the greatest engineering mysteries of early Roman civilization. One of the first mysteries surrounding the Wall of Romulus involves the stonework itself. The wall was built primarily from volcanic tuff quarried from the hills surrounding Rome. Tuff is relatively soft immediately after extraction, but hardens over time when exposed to air. Ancient Roman builders appear to have understood this property in extraordinary detail. Several surviving blocks show flat contact surfaces with the deviations measuring only a few millimeters. For an 8th century BCE society using primitive bronze and early iron tools, such precision is difficult to explain. In some sections, the stones interlock tightly enough that even modern blades struggle to pass between them. Archaeologists compared the fitting techniques to later Etruscan and even Incan polygonal masonry. Yet the Wall of Romulus predates many of those advanced traditions. Some researchers argue the builders may have used abrasive volcanic sand combined with water and repetitive grinding methods, rather than relying solely on chisels. Others believe wooden frames and weighted lever systems were used to stabilize cuts with surprising accuracy. The real mystery is not merely that the stones were shaped, but that they were shaped consistently across large defensive sections without modern geometry, lasers or steel tools. Compared to other settlements in Italy during the same period, Rome's earliest fortification appears technologically ahead of its neighbours by generations. Rome was not built on ideal terrain. The city developed over layers of volcanic ash, clay, and unstable sediment near the Tiber River. Structures built on such ground usually crack, tilt, or collapse over centuries. Yet portions of the Wall of Romulus survived for nearly 2,700 years. Excavations revealed something unexpected beneath the visible stone layers: a primitive shock-absorbing foundation system. Instead of placing stones directly onto solid earth, the builders created layered beds of compacted gravel, fragmented tuff and drainage gaps. These gaps allowed water to escape while distributing pressure more evenly across unstable terrain. Modern engineers studying the structure noticed similarities to seismic mitigation principles used in later Roman roads and even some modern earthquake-resistant foundations. Laboratory analysis of surviving sublayers showed evidence of deliberate grading in particle size. Larger fragments were placed lower, while smaller compacting materials were layered above. This reduced soil movement and prevented catastrophic shifting during seasonal flooding. The engineering resembles systems later perfected in Roman roads such as the Via Appia, yet the Wall of Romulus predates those achievements by centuries. Some experts believe early Roman builders may have gained practical geological knowledge through repeated flood disasters around the Tiber Valley. Others argue the techniques were inherited from the Etruscans, whose engineering abilities remain partially mysterious themselves. Either way, the foundation system suggests an understanding of terrain mechanics far beyond what historians once expected from early Rome. Another mystery lies in the volcanic tuff itself. Modern geological studies found that certain sections of the wall used high zeolite tuff, a material naturally resistant to moisture and thermal stress. Zeolites are microporous minerals capable of trapping water and reducing long-term cracking. The Romans could not have known the chemistry scientifically, yet they consistently selected stone from quarries with unusually durable mineral compositions. Over centuries, exposure to air triggered chemical hardening reactions within the volcanic material. Instead of weakening rapidly like ordinary sedimentary stone, some tuff blocks became denser over time. Researchers compared samples from the Wall of Romulus to stone used in later Roman structures such as the Servian Wall and portions of the Colosseum substructure. Surprisingly, some early blocks showed durability levels approaching those from much later imperial projects. This raises a disturbing possibility. The builders may have possessed generations of empirical geological knowledge long before formal Roman engineering manuals existed. Ancient workers may have tested quarry stone through observation over decades, identifying which material resisted water, heat, and erosion best. If true, Rome's earliest engineers were conducting primitive materials science centuries before the concept even existed. The positioning of the Wall of Romulus may be even more mysterious than the wall itself. Rather than forming a simple circular barrier around houses, many sections follow elevated ridges around the Palatine Hill with carefully calculated sightlines. From several preserved points, defenders could monitor multiple approach routes simultaneously. Military historians studying the layout notice similarities to later defensive theories involving overlapping visual control zones. Certain angles allowed observers to detect movement near river crossings and lower valleys long before enemies approached the core settlement. For a supposedly primitive hilltop community, the strategic planning appears unusually advanced. Comparisons with early Greek colonies from the same era show that many lack defensive optimization of this complexity. Rome's earliest fortification already demonstrates awareness of elevation advantage, surveillance geometry, and terrain funneling. Some archaeologists speculate the wall was not built all at once, but evolved through repeated military conflicts. Burn layers discovered beneath repair phases suggest attacks or raids occurred multiple times during the city's earliest centuries. Each reconstruction phase appears more refined than the previous one, almost as though Rome used the wall itself as a long-term engineering experiment. The Wall of Romulus was not merely military architecture, it was psychological architecture. According to Roman tradition, the city boundary, called the Pomerium, possessed sacred power. Crossing it unlawfully was considered a direct attack against the city's divine order. Legend claims Romulus killed his brother Remus after he mocked the defensive boundary by leaping over it. Whether true or not, the story reveals something important. The wall functioned as both a physical and symbolic technology of control. Anthropologists comparing Rome with other ancient civilizations noticed that early Roman identity became deeply tied to protected boundaries. The walls separated civilization from chaos, citizen from outsider, sacred land from hostile territory. Unlike many Bronze Age settlements where walls served mainly defensive purposes, Rome transformed fortifications into instruments of political unity and religious authority. The engineering of the structure, therefore, cannot be separated from the engineering of belief itself. Excavations reveal repeated destruction and rebuilding at Wall of Romulus. Burn layers, cracked stones, and replacement masonry suggest the wall endured multiple disasters over centuries. But each reconstruction introduced better engineering. Later sections used stronger stone alignment, improved drainage, and thicker support bases, showing that Roman builders were refining techniques through experience and failure. Some methods seen in the earliest layers later vanished, only to reappear centuries afterward in advanced Roman military architecture. This suggests parts of early Roman engineering knowledge may have been lost or forgotten over time. The Wall of Romulus may therefore preserve some of the oldest experimental engineering techniques in Roman history. Do you think the Wall of Romulus was built using knowledge far ahead of its time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Steam still rises from the water every single day beneath the city of Bath in southwestern England. More than 2,000 years after Roman engineers first enclosed the spring with stone, the water continues to emerge from the earth at nearly 46 degrees Celsius, pushing over 1 million litres to the surface every day. Modern geothermal spas use electric pumps, pressure sensors, reinforced concrete, and computerized flow systems to maintain stable operation. The Roman baths used none of them, and yet the system survived. What makes the Roman baths extraordinary is not simply their age. It is the possibility that Roman engineers understood underground heat, mineral corrosion, structural pressure, airflow, and water control at a level historians once believed impossible for the ancient world. The site was built around a natural hot spring during the 1st century AD, shortly after the Roman conquest of Britain. Archaeologists believe Roman surveyors identified the spring because of constant steam rising through the marshlands of the River Avon Valley. Excavations beginning in the late 19th century uncovered massive submerged foundations, collapsed chambers, lead pipelines, and one of the most sophisticated thermal complexes ever discovered in the Roman Empire. But the deeper archaeologists dug, the stranger the engineering became. The first mystery is the spring itself. The hot water beneath Bath is created by an unusually deep geothermal cycle. Rainwater seeps underground through limestone faults and travels down nearly 3 to 5 kilometers beneath the surface. There, geothermal heat warms the water before underground pressure forces it upward through fractures in the rock. Modern hydrogeologists estimate this process can take thousands of years for a single drop of water to complete. What remains difficult to explain is how Roman engineers located the most stable pressure zone without modern geological tools. If the retaining walls had been placed incorrectly, sediment could have blocked the spring, pressure could have collapsed the chambers, or temperature fluctuations could have destabilized the entire system. Instead, the Romans constructed a reservoir lined with massive lead sheets and stone blocks, capable of containing constant thermal expansion for centuries. Even today, engineers studying geothermal systems compare Bath to passive thermal regulation used in modern spa infrastructure. The second mystery involves the materials. The water flowing through the Roman baths is rich in dissolved minerals including calcium sulfate, sodium chloride, and magnesium compounds. Under modern conditions, mineral-rich thermal water rapidly destroys pipes and concrete through scaling and chemical corrosion. Many modern geothermal facilities require continuous maintenance to prevent mineral buildup from choking entire systems. Yet large portions of the Roman baths survived nearly 2 millennia. Scientists analyzing Roman mortar discovered that the builders used mixtures containing lime, crushed brick, and volcanic ash in carefully balanced proportions. These mixtures created pozzolanic reactions, chemical processes that continue strengthening the concrete when exposed to water. In some microscopic studies, Roman concrete exposed to seawater or thermal water actually became more chemically stable over time. This directly contrasts with modern Portland cement, which often weakens after prolonged exposure to hot mineral-rich water. At Bath, the survival of underground walls exposed to heat and flowing minerals for nearly 2,000 years remains one of the strongest examples of Roman material engineering outperforming many modern equivalents. The third mystery lies beneath the floor. The Roman baths operated using a hypercore system, essentially a giant ancient heating network hidden under stone surfaces. Workers maintained furnaces that pushed hot air beneath elevated floors supported by hundreds of brick pillars. Heat travelled through hollow wall channels before exiting through roof vents. The result was astonishingly advanced. The floors remained warm, moisture levels stayed controlled, and steam circulated through different chambers with remarkable consistency. Temperature could be adjusted between hot, warm, and cold rooms in ways surprisingly similar to modern climate-controlled spas. Engineers today recognize the same principles in radiant floor heating and HVAC airflow systems involving convection, pressure circulation, thermal distribution, and humidity management. What makes the Roman system remarkable is that it functioned entirely without electricity or mechanical pumps. The entire complex relied purely on geometry, airflow, and thermal pressure gradients. Some researchers argue the Romans may have developed practical engineering knowledge of heat behavior centuries before formal thermodynamics existed as a science. Another major mystery involves lead. Large sections of Roman plumbing used lead pipes, a fact that has puzzled historians for decades. Modern medicine identifies lead as highly toxic, especially through drinking water systems. Yet Roman cities operated extensive lead-based plumbing networks across Europe for centuries. At Bath, mineral-rich water may hold the answer. Studies suggest the high calcium content of the spring water quickly formed thick mineral coatings inside the pipes, dramatically reducing direct contact between water and lead surfaces. Similar effects are observed in some modern water systems where carbonate deposits create protective barriers inside old pipelines. This accidental chemical protection may explain why catastrophic mass poisoning evidence remains surprisingly limited in many Roman settlements. Even so, debate continues among archaeologists, toxicologists, and historians. Some argue chronic low-level exposure still affected Roman populations in ways difficult to detect today. The architecture itself presents another puzzle. Roman bath chambers generated enormous amounts of steam every day. Constant condensation should have weakened ceilings, destabilized stone joints, and accelerated structural decay. Yet many arches and vaulted spaces remained standing for centuries. Researchers studying Roman vault geometry discovered that curved ceilings may have been intentionally designed to redirect condensation and distribute moisture evenly across surfaces. The arches also disperse structural stress while allowing rising hot air to circulate naturally through upper chambers. Modern sauna complexes use remarkably similar airflow principles, but Roman builders achieved this using only stone, fired clay, lime mortar, and geometric calculations. No steel reinforcement existed. No computer simulations guided the construction. Everything depended on experience, observation, and mathematical intuition. The baths also reveal an unsettling connection between engineering and religion. The complex was dedicated to Sulis Minerva, a fusion of a local Celtic goddess and the Roman goddess Minerva. To ancient visitors, the spring was not merely geothermal activity, it was sacred. Excavations uncovered hundreds of curse tablets buried in the water. These thin sheets of lead were inscribed with requests for divine punishment against thieves, rivals, or traitors. Many were intentionally thrown into the deepest parts of the spring where water pressure was strongest. To the Romans, the rising thermal waters may have represented a gateway between worlds. This blending of advanced engineering with supernatural belief appears repeatedly across ancient civilizations. The Maya aligned temples with astronomical cycles. Egyptian pyramids integrated celestial orientation into monumental architecture. At Bath, hydraulic engineering became inseparable from ritual power. One of the most surprising discoveries came from modern scanning technology. Laser mapping and underground surveys revealed that much of the Roman hydraulic infrastructure extended deeper and farther than earlier archaeologists realized. Hidden drainage tunnels, overflow channels, and pressure release systems suggest the complex was designed not only to transport water, but also to survive long-term geological instability. This level of planning resembles modern civil engineering far more than traditional ancient construction. Comparisons with other Roman sites only deepen the mystery. At Pompeii Archaeological Park, volcanic ash preserved water systems capable of regulating fountains and baths across an entire city. At Aqueduct of Segovia, stone arches transported water over 15 kilometers without mortar. At Chedworth Roman Villa, Hippocaust systems maintained heated floors through British winters nearly 2,000 years ago. But Bath combined all of these technologies together: geothermal extraction, thermal regulation, hydraulic engineering, structural moisture control, and mineral-resistant construction. Few ancient sites demonstrate such an integrated understanding of environmental engineering. Just north of modern St Albans lie the ruins of Verulamium Theatre, the only fully excavated Roman theatre in Britain. The structure was first identified in the 19th century, but major excavations between the 1930s and 1960s revealed something unexpected beneath the soil of ancient Roman Verulamium, a theatre far more technologically advanced than historians once believed. Built around the 2nd century AD, the theatre could hold nearly 2,000 spectators. That may sound modest compared to Rome's giant amphitheatres, but for Roman Britain, a distant frontier province surrounded by cold rain, unstable ground and limited resources, the scale was extraordinary. Archaeologists uncovered carefully engineered drainage channels, unusually durable mortar, mathematically balanced seating geometry, and acoustic properties that still puzzle engineers today. Unlike the Colosseum in Rome, which relied on massive imperial resources, Verulamium Theatre was constructed at the northern edge of the empire. Yet many of its engineering solutions appear remarkably sophisticated for such a remote location. And that raises the central mystery. How did Roman engineers in ancient Britain create a theatre whose sound projection, water management, and structural stability still outperform many medieval structures built more than 1,000 years later? One of the strangest discoveries at Verulamium is its acoustic performance. Even in its ruined state, researchers found that voices projected from the stage remain surprisingly clear across much of the seating area without electronic amplification. Modern acoustic studies show that the semicircular seating arrangement, combined with the angle of the retaining walls, helped concentrate sound waves towards spectators. The geometry resembles principles used in modern acoustic shell design and opera halls. But here's the problem. Roman Britain had no advanced mathematical acoustic theory. no sound simulation software, and no precision instruments capable of modelling wave reflection. Yet the theatre's dimensions appear almost optimised. The seating slope is steep enough to prevent major sound loss while still maintaining visibility. The curved orchestra area reduces echo distortion. Even the wall placement may have acted as a primitive resonance chamber. Comparisons with other Roman theatres reveal something unusual. Many larger theatres across Europe lost acoustic efficiency due to later reconstruction or poor local materials. Verulamium, despite being smaller and built in wetter conditions, achieved remarkable clarity. Some researchers believe Roman architects inherited acoustic knowledge from Greek theatre builders, but others argue that Verulamium demonstrates practical engineering experimentation far beyond what written Roman texts describe. Even today, archaeologists cannot fully explain how builders achieve such precision using only manual surveying tools. Britain's climate is destructive to ancient masonry. Freeze-thaw cycles crack stone. Rainwater weakens mortar. Ground moisture destabilizes foundations. Yet large portions of Verulamium theatre survive nearly 1,800 years. Why? Analysis of surviving mortar revealed a sophisticated mixture of lime, crushed brick, stone aggregates and ceramic particles. Under microscopic examination, some samples showed signs of pozzolanic chemical reactions, the same process responsible for the legendary durability of Roman concrete. The mystery is that Britain lacked the volcanic ash commonly used in Italy to create true Roman hydraulic concrete. So how did builders replicate similar properties? Some scientists believe local engineers developed substitute mixtures using crushed tile and fired clay. When combined with lime, these materials may have created calcium-aluminum silicate compounds capable of resisting moisture damage. Modern concrete often deteriorates after only 50 to 100 years under severe environmental stress. Parts of Verulamium's foundation survived almost 20 centuries. Researchers from several material science studies have even suggested that Roman concrete may possess microscopic self-healing properties. When cracks formed, mineral reactions inside the mortar slowly sealed them over time. If true, Roman engineers in Britain may have unknowingly produced a long-lasting material technology centuries ahead of medieval Europe. Perhaps the greatest engineering mystery lies underground. Excavations uncovered an elaborate drainage network beneath the theatre, including stone-lined channels, runoff paths, and sloped water exits connected to the wider infrastructure of Roman Verulamium. This system was essential because the theatre stood in a region with heavy rainfall and waterlogged soil. Without drainage, the seating foundation should have collapsed centuries ago. Instead, much of the structure remained stable. Engineers studying the site noticed that water flow appears carefully controlled through gravity gradients. The channels were angled precisely enough to prevent stagnant water accumulation, while reducing erosion pressure against the foundations. Some stones inside the drainage tunnels were fitted so tightly that very little mortar was needed. Similar techniques appear in Roman aqueduct systems across southern Europe. The comparison becomes even more surprising when viewed against medieval Britain. Many medieval stone buildings suffered severe subsidence due to poor drainage understanding. Yet Roman builders at Verulamium had already implemented systems resembling modern water management engineering. No surviving Roman text fully explains how provincial engineers designed such effective underground infrastructure in hostile northern climates. At first glance, Verulamium appears to be a simple performance venue, but excavations revealed unusual backstage chambers, narrow corridors, concealed entryways, and reinforced substructures beneath the stage. Some archaeologists now suspect the theatre was designed for mechanical stage effects. Roman writers describe devices capable of lifting actors onto stages, creating sudden appearances, and simulating divine interventions during performances. In Mediterranean cities, such machinery was relatively common, but finding possible evidence of similar technology in Britain shocked historians. Certain foundation sections at Verulamium are thicker than structurally necessary. Some corridors seem positioned specifically for hidden movement behind performances. Small enclosed rooms may have housed counterweight systems or ritual equipment. If these interpretations are correct, then Roman Britain possessed far more advanced theatrical engineering than previously assumed. This also changes how historians view frontier provinces. Instead of isolated outposts struggling for survival, cities like Verulamium may have been technologically connected to the core of the empire through highly organized engineering networks. One of the most difficult questions concerns construction logistics. Archaeologists estimate that thousands of tons of stone, brick, timber and earth were transported and assembled during the theatre's development phases. Yet despite manual labor and primitive transport systems, the structure maintained remarkable geometric consistency. Brick dimensions remain highly standardized. Seating curvature follows smooth mathematical arcs. Foundation alignment stayed accurate across multiple expansion phases. Roman surveyors likely used Groma instruments measuring rods, plumb lines, and astronomical alignment methods. But many researchers argue those tools alone should not have produced such consistency at this scale. Comparisons with later medieval theatres reveal an uncomfortable reality. In some engineering aspects, Roman construction quality in Britain was not matched again for centuries. This suggests Roman organizational systems may have been just as important as their materials technology. Labor coordination, modular construction methods, and standardized measurements allowed complex projects to be replicated across vast distances. Verulamium was not merely a local theatre. It may have been part of a giant technological system spreading Roman engineering knowledge across an empire stretching over 5 million square kilometers. Do you think Verulamium Theatre was simply abandoned by time, or deliberately buried to erase part of Rome's forgotten past? Share your theory in the comments below. Between the Firth of Forth and the Firth of Clyde in central Scotland, the Romans built a 63-kilometre barrier that should not have survived. Unlike the massive stone structure of Hadrian's Wall, the Antonine Wall was made largely from earth, turf, timber, and compressed organic material. Yet nearly 2,000 years later, parts of its shape are still visible beneath the cold rain and wetlands of Scotland. Modern engineers still debate how a living wall built from soil could resist one of the harshest climates in Roman Britain. The wall was officially identified through antiquarian surveys in the 18th century, but major excavations accelerated during the 19th and 20th centuries. Archaeologists uncovered forts, drainage systems, distant slabs, military roads, and layers of compacted turf blocks cut with astonishing uniformity. Aerial photography later revealed how precisely the wall followed Scotland's terrain. The greatest mystery surrounding Antonine Wall is not military strategy, it is material science. Unlike Hadrian's Wall, which used roughly 1.3 million tons of stone, Antonine Wall relied heavily on stacked turf blocks, placed over a stone foundation and defensive ditch. Roman engineers essentially built a gigantic organic barrier stretching across Scotland around 142 CE under Emperor Antoninus Pius. To modern engineers, this sounds almost impossible. Scotland's climate is brutally hostile to earthworks. Annual rainfall in parts of the wall's route exceeds 1,000 millimeters. Winters bring freeze-thaw cycles capable of cracking stone, while saturated ground causes landslides and soil collapse. Most ancient turf fortifications disappear within centuries, yet Antonine Wall survived nearly 2 millennia. Excavations revealed that the Romans did not simply pile dirt into a mound. Turf blocks were cut into standardized sections and layered in repeating patterns. Some archaeologists compare the structure to giant biological bricks. The turf retained root systems and organic fibers, which may have acted like natural reinforcement mesh inside modern composite concrete. Several preserved sections show evidence of alternating compacted layers designed to redirect water outward, rather than allowing moisture to penetrate deeply into the wall. This resembles principles used in modern geotechnical engineering and flood embankment construction. The most shocking detail is density. Tests on surviving sections found that some layers were compressed so tightly they resisted erosion far better than expected for ordinary soil. Roman soldiers may have repeatedly compacted each layer using thousands of footsteps, wooden pounders, and controlled moisture levels. Some engineers now believe the wall behaved less like a rigid barrier and more like a shock-absorbing structure. Stone walls crack under shifting wet ground. Turf walls flex. During heavy rain and freezing expansion, Antonine Wall may have redistributed stress instead of resisting it directly. This idea sounds surprisingly modern. Today, engineers designing sustainable flood defenses sometimes use living embankments, reinforced with vegetation because roots stabilize soil naturally. Antonine Wall may represent one of the earliest large-scale examples of this concept ever attempted. Yet a major mystery remains unanswered. How did Roman engineers understand these environmental mechanics without modern geology? No surviving Roman text explains the precise construction formula. There are no manuals describing turf moisture ratios, compression techniques, or drainage calculations. The engineering knowledge behind the wall appears almost invisible. The second great mystery is water control. Without advanced drainage, the wall would have collapsed rapidly into mud. Scotland's terrain includes wetlands, soft clay, and uneven glacial deposits. Building a 63-kilometre earthwork across such land should have been a logistical disaster. Instead, archaeologists discovered carefully prepared foundations beneath many sections. Gravel layers, stone platforms, and drainage channels redirected water away from the turf core. In some areas, the Romans even modified natural slopes to maintain stability. The military way, the Roman road running behind the wall, may also have functioned as part of a broader drainage network. Slight elevation differences allowed water to move laterally instead of pooling beneath the structure. Modern laser terrain mapping revealed something astonishing. Many sections were placed along naturally stable ridges with lower water saturation. This means Roman surveyors likely understood hydrology at a highly advanced practical level. Compared with many medieval fortifications that deteriorated rapidly in wet environments, Antonine Wall demonstrates environmental adaptation centuries ahead of its time. The wall's placement creates another mystery. The Romans built Antonine Wall across highly variable terrain, yet the alignment remains remarkably efficient. Forts were positioned at intervals that maintained communication visibility, often allowing signal transmission by fire or smoke across long distances. Modern geographic analysis suggests Roman engineers intentionally selected elevated ground while minimizing exposure to unstable soil. Achieving this across 63 kilometers without aerial mapping appears extraordinarily difficult. Some historians argue Roman surveyors used sophisticated optical tools such as the groma and chorobates. But others believe the precision visible in the wall exceeds what those devices alone should realistically achieve in Scotland's weather conditions. Even more intriguing is the consistency of construction modules. Fortlets, defensive ditches, and turf widths follow repeated dimensional patterns, suggesting standardized engineering templates similar to modular construction systems today. Building Antonine Wall may have required one of the largest coordinated engineering operations in Roman Britain. Historians estimate tens of thousands of soldiers participated in the project. Massive quantities of turf had to be cut, transported, stacked, compacted, and maintained. Timber, gravel, and stone foundations also had to be gathered from surrounding regions. Unlike urban Roman projects near Mediterranean trade routes, this construction occurred in hostile frontier territory with cold weather, tribal resistance, and unstable supply lines. Some calculations suggest millions of turf blocks may have been used. yet the wall was completed in little more than a decade. That speed continues to puzzle archaeologists. Roman military efficiency was legendary, but Antonine Wall required precision engineering under environmental conditions far worse than those faced during many continental Roman projects. Distant slabs discovered along the frontier indicate different Roman legions competed to complete assigned sections. These carved stones recorded construction lengths with almost propagandistic pride. But some researchers suspect the slabs served another purpose: standardized engineering markers for measuring progress, labor distribution, and structural consistency across the frontier. What do you think? Was Antonine Wall abandoned because of climate, logistics, or something far more mysterious? Share your thoughts in the comments below. In the Dobruja region of modern Romania, near the lower Danube frontier, Ibida was once one of the largest Roman Byzantine fortified cities in southeastern Europe. Yet for centuries, almost nobody knew how advanced it truly was. Beneath collapsed walls and buried streets, archaeologists uncovered evidence of engineering techniques, water systems, and metallurgical technologies that still raise questions today. The ruins of Ibida were first identified in the late 19th century, but major excavations accelerated only in the early 2000s after aerial surveys and geomagnetic scans revealed the enormous scale of the buried city. What researchers found shocked many historians. Massive fortification walls stretched for more than 2 kilometers around a settlement covering nearly 24 hectares. Towers, underground drainage systems, workshops, military structures, and industrial zones suggested that Ibida was not a minor frontier outpost, but a heavily engineered strategic center protecting the Byzantine frontier near the Danube. One of the first mysteries surrounding Ibida is the durability of its defensive walls. The fortifications were built using alternating layers of stone blocks, crushed brick, lime mortar, and compacted rubble. At first glance, the structure resembles standard late Roman military architecture. But detailed structural analysis revealed something unusual. Many sections of the wall contain inner cores made from semi-flexible materials rather than solid stone. Engineers studying the ruins believe this design may have functioned as a shock absorption system. In modern earthquake-resistant engineering, layered materials are often used to disperse vibration energy and reduce cracking. Ibida's walls appear to operate on a surprisingly similar principle. This becomes even more mysterious when considering the climate conditions of Dobruja. Temperatures in the region can fluctuate dramatically between freezing winters and intense summer heat. Normally, repeated expansion and contraction would fracture ancient masonry over centuries, yet parts of Ibida's fortifications remain structurally stable after nearly 1,500 years. Researchers compared the walls with Roman frontier forts in Britain and Germania and found that some surviving sections at Ibida show lower rates of thermal cracking despite harsher seasonal shifts. Some archaeologists suspect the builders may have intentionally mixed volcanic minerals or specially prepared lime compounds into the mortar to improve elasticity and moisture resistance. However, no complete reconstruction of the original formula has been achieved. The city's water management system presents another engineering mystery. Excavations uncovered underground drainage channels constructed with carefully angled stone linings that still function during heavy rainfall today. Laser measurements revealed remarkably consistent gradients throughout several surviving channels, showing that the builders understood hydraulic flow with impressive precision. This is particularly difficult to explain because Ibida existed in an environment with alternating drought and freezing conditions. Water trapped underground during winter should have expanded into ice and destroyed many of the channels, yet portions survived almost intact. Some researchers believe the system may have included hidden ventilation shafts that reduced internal pressure caused by freezing water. Others suspect the use of waterproof mineral coatings similar to those found in Byzantine cisterns at Constantinople. Comparisons with medieval drainage systems reveal how advanced this was. In many European cities built nearly 1,000 years later, underground drainage frequently collapsed due to poor slope calibration or water pressure damage. At Ibiza, some channels still preserve their original alignment despite centuries of erosion and seismic activity. But perhaps the most disturbing mystery lies beneath the industrial district of the city. Archaeologists excavating near the southern defensive sector discovered evidence of large-scale metallurgical activity. Furnaces, slag deposits, iron fragments, charcoal concentrations, and workshops likely connected to military production. At first, researchers assumed these were ordinary frontier blacksmith operations. Then laboratory analysis began revealing anomalies. Several slag samples indicate furnace temperatures that may have exceeded what standard Roman bloomery furnaces were believed capable of sustaining in remote frontier settlements. Certain iron fragments also displayed unusually consistent carbon distribution, suggesting more advanced thermal control than expected for the period. To understand why this matters, it is important to compare Ibiza with known Roman metallurgical centres. Traditional Roman bloomery furnaces generally operated between approximately 1,100 and 1,250 degrees Celsius. Temperatures above this range become difficult to maintain without carefully controlled airflow systems. Yet some material traces at Ibiza suggest localized temperatures may have approached levels associated with partial steel production techniques. That should not have been possible in a relatively isolated frontier city lacking large urban infrastructure. Some metallurgists studying the site propose that the workshops used multi-stage airflow systems powered by synchronized bellows. Others suggest underground air channels may have amplified oxygen intake naturally using pressure differences caused by wind moving across the fortress walls. Similar passive airflow concepts appear in a few ancient industrial sites, but evidence at Ibiza remains incomplete. Even more mysterious is the fuel efficiency implied by the remains. Maintaining extreme temperatures requires enormous quantities of charcoal. Yet the surrounding environment does not appear capable of supporting industrial-scale deforestation for long periods. This has led to speculation that Ibiza's metallurgists may have developed unusually efficient furnace insulation or combustion chamber designs that minimized heat loss. Some furnace fragments show traces of vitrification, partial glass-like melting caused by repeated exposure to extreme heat. Comparable effects are seen in later medieval steel production centres, but rarely at Roman frontier sites. This raises a controversial possibility. Ibiza's workshops may have been experimenting with metallurgical methods more sophisticated than historians traditionally associate with late Roman military provinces. The military implications are significant. Ibiza occupied a strategic location near the Danube frontier during centuries of invasions by Goths, Huns, Avars, and Slavic groups. Advanced metal production could have allowed rapid manufacturing of weapons, armor fittings, tools, and defensive hardware without relying entirely on distant imperial supply chains. Some historians now suspect the city functioned as a hidden industrial fortress, part military base, part engineering centre, supporting Byzantine defence operations across the lower Danube region. Yet the strangest mystery is how Ibiza disappeared. Despite its massive walls and strategic importance, the city nearly vanished from written history after the 6th and 7th centuries. No surviving chronicle clearly explains its final destruction. Archaeologists found evidence of fires, collapsed buildings, emergency repairs, and sudden abandonment suggesting repeated invasions or long periods of instability. Climate change may also have played a role. Studies around the lower Danube indicate that colder temperatures and shifting rainfall during the late Antique Little Ice Age weakened agriculture and frontier economies across the Byzantine world. Combined with constant attacks, even a technologically advanced city like Ibiza may have become impossible to sustain. Unlike Pompeii or Constantinople, Ibiza left behind almost no historical narrative. Instead, it survives as buried ruins whose advanced walls, drainage systems, and mysterious industrial workshops continue to challenge assumptions about ancient frontier civilizations. The deeper archaeologists investigate Ibiza, the more the site feels less like a forgotten border town, and more like a lost military engineering center far ahead of its time. What do you think Ibiza truly was? Just a forgotten Roman frontier city, or evidence that ancient military engineering was far more advanced than history admits? Leave your theory in the comments below. Bignar Roman villa was discovered in 1811 after a local farmer accidentally struck a buried mosaic while ploughing a field in West Sussex, southern England. At first, the colourful stones looked like random fragments beneath the soil, but as excavation began, archaeologists uncovered one of the largest and most sophisticated Roman villas ever found in Britain. Beneath quiet farmland lay massive reception halls, heated rooms, advanced drainage systems, and mosaics so well preserved that many experts still struggle to explain how they survived nearly 2,000 years in Britain's wet climate. What makes Bignar mysterious is not simply its wealth. It is the level of engineering hidden inside a remote corner of the Roman Empire. Britain was considered one of Rome's harshest provinces. Cold, rainy, unstable, and far from the Mediterranean world where Roman architecture evolved. Yet Bignar appears to have replicated technologies comparable to elite villas in Italy itself. Some researchers now believe the site preserves evidence of forgotten Roman material science, adapted specifically for Northern Europe. One of the greatest mysteries involves the villa's hypocaust heating system. Roman engineers constructed raised floors supported by hundreds of small brick pillars, creating hollow chambers beneath the rooms. Hot air from furnaces circulated underneath the floors and through channels inside the walls, producing central heating centuries before modern Europe developed similar systems. The engineering precision required was extraordinary. Temperatures had to remain balanced across multiple rooms without cracking floors or trapping smoke inside the structure. Archaeological reconstructions suggest parts of the villa could maintain indoor temperatures above 18 degrees Celsius, even during cold British winters. That would have made Bignar dramatically warmer than most medieval stone buildings constructed over 1,000 years later. What confuses engineers today is the durability of the system. The brick pillars beneath the floors endured repeated cycles of heat, cooling, and moisture for centuries. In modern structures, thermal expansion often weakens mortar and causes fractures over time. Yet parts of Bignar's foundations remained intact after nearly 2 millennia underground. Some samples of Roman mortar from Britain show unusually high resistance to water penetration and chemical erosion, leading researchers to suspect the builders modified traditional Roman concrete formulas for Britain's damp conditions. Comparisons with later English architecture make the mystery even stranger. Many medieval castles built in Britain between the 11th and 14th centuries suffered severe moisture damage, collapsing walls, or unstable foundations despite being far newer. But sections of Bignar's infrastructure survived beneath saturated soil for almost 1,800 years. This raises an uncomfortable question for historians. Did Roman builders in Britain possess construction knowledge later generations lost completely? The mosaics inside the villa deepen the mystery further. Bignar contains some of the finest Roman mosaics ever discovered in Northern Europe, including the famous depiction of Ganymede being carried by Jupiter's eagle. The detail is astonishing. Thousands of tiny tesserae, carefully cut coloured stones and tiles, were arranged with such precision that the images appear shaded almost like modern pixel art. But the real puzzle is preservation. Britain's climate is one of the worst possible environments for ancient mosaics. Constant humidity, groundwater movement, and temperature fluctuations normally destroy pigments and lift flooring apart over centuries. Yet, many mosaics at Bignor retained strong reds, blacks, yellows, and whites, long after comparable Roman floors elsewhere faded badly. Scientists studying the site discovered that the flooring rested on multiple carefully engineered layers. Beneath the visible mosaic sat compacted stone, mortar, crushed brick, and drainage materials designed to prevent trapped moisture from rising upward. Modern conservation experts note that even slight failures in drainage would have caused catastrophic cracking over time. The survival of these floors suggests Roman builders understood hydrology and soil behavior in far greater detail than previously assumed. Some archaeologists compare Bignor's preservation with sites like Pompeii. Pompeii's mosaics were protected suddenly by volcanic ash, effectively sealing them from weather exposure. Bignor had no such protection. It survived through centuries of rainfall, seasonal freezing, agricultural activity, and shifting groundwater. In some ways, the preservation at Bignor is harder to explain scientifically than the preservation at Pompeii itself. The villa's drainage network may be the most underrated engineering mystery of all. Excavations revealed channels, slopes, and carefully graded surfaces directing water away from key rooms. Modern laser surveys found that some floor inclinations were controlled within remarkably small margins. That precision matters because even tiny pooling areas can destroy masonry over long periods. Roman engineers appear to have designed the villa almost like a living environmental system, balancing heat, moisture, airflow, and structural pressure together. This resembles concepts used in modern sustainable architecture far more than what people normally imagine about ancient Britain. Another unresolved question involves the enormous wealth behind the villa. Bignor was not a military fort or administrative centre. It was a luxury estate located in rural southern England, far from Rome. Yet it contained imported materials, highly trained craftsmen, geometric planning, and elite artistic decoration comparable to villas found much closer to the imperial core. Historians still debate who owned it. Some theories suggest the villa belonged to a Romano-British aristocrat connected directly to imperial trade networks. Others believe it may have functioned as a political centre for wealthy elites controlling agricultural production across the region. But the scale of investment remains difficult to explain. Transporting specialized craftsmen and materials across the Roman Empire into one of its coldest provinces would have required enormous logistical coordination. The villa also reveals evidence of advanced mathematical planning. The mosaics contain repeating geometric symmetries requiring accurate measurement systems. Room layouts align with proportional ratios commonly used in Roman architecture. Researchers studying Roman surveying tools believe builders may have used calibrated measuring rods, plumb systems, and angular calculations precise enough to maintain near-perfect floor alignment across large interior spaces. Some scholars argue that Roman Britain has long been underestimated technologically because many surviving structures are fragmentary. Sites like Bignor challenge the idea that the province was culturally inferior to mainland Europe. Instead, they suggest Roman engineers adapted their technologies aggressively to local environmental challenges, creating hybrid systems specifically suited for Britain's climate. Perhaps the strangest aspect of Bignor Roman villa is what happened after Rome collapsed. By the 5th century, much of Britain lost access to the engineering systems seen at the villa. Large-scale heated floors disappeared. Mosaic production declined sharply. Sophisticated moisture control techniques became rare. In some regions, construction quality visibly deteriorated for centuries afterward. This technological regression remains deeply unsettling to historians. Civilization is often imagined as a straight line of progress, but Bignor suggests ancient societies sometimes mastered engineering techniques that later cultures failed to preserve. Certain Roman formulas, architectural methods, and environmental designs may have effectively vanished after imperial administration collapsed. Even today, modern researchers continue analysing microscopic structures inside Roman mortar and flooring layers, hoping to understand why these materials survived so long. Some tests indicate self-healing chemical reactions inside Roman concrete mixtures, where minerals react with water to seal microcracks over time. Similar mechanisms have been identified in Roman harbour concrete around the Mediterranean, but their appearance in Britain raises new questions about how widely this knowledge spread across the empire. Northern England, stretching nearly 117 kilometres from the River Tyne to the Solway Firth, Hadrian's Wall was officially identified in the 18th and 19th centuries through large-scale archaeological surveys led by antiquarians such as John Clayton. Built around 122 AD under Emperor Hadrian, the structure cut directly across Roman Britain. Excavations later revealed forts, hidden drainage systems, workshops, roads, and engineering layers buried beneath centuries of soil. What shocked archaeologists was not simply the wall's size, but the level of technical precision hidden inside a frontier built almost 2,000 years ago. One of the greatest mysteries surrounding Hadrian's Wall is how Roman engineers maintained such remarkable alignment across brutal terrain without modern surveying equipment. The wall crossed hills, marshes, rivers, and unstable ground, yet many sections remain astonishingly straight for long distances. Modern engineers comparing Roman measurements with satellite analysis discovered that some stretches deviate by only a tiny margin, despite being built across uneven landscapes. For comparison, many medieval fortifications built more than 1,000 years later show significantly larger structural inconsistencies. Roman surveyors likely used a tool called the groma, combined with astronomical positioning and elevated observation points. However, historians still debate how they achieved this level of consistency across such enormous distances in northern Britain's constantly shifting weather conditions. The mystery deepens when studying the wall's foundations. In some areas, Roman builders changed the wall's width mid-construction while still preserving structural stability. Originally planned at nearly 3 meters thick in stone sections, parts were later reduced to around 2.4 meters, yet the load distribution remained surprisingly effective. This suggests Roman engineers were dynamically recalculating material efficiency during construction, something rarely associated with ancient military architecture. Even more puzzling is the speed of construction. Archaeologists estimate that over 15,000 Roman soldiers participated in the project. Based on surviving construction evidence, large sections may have been completed within only 6 years. Considering the scale of excavation, quarrying, transportation, and stone cutting required, many historians argue that the logistical coordination resembles an industrial-era military project more than an ancient frontier wall. Perhaps the most fascinating engineering mystery involves the wall's mortar and stone durability. Northern England experiences constant rainfall, freeze-thaw cycles, humidity, and powerful winds. Under similar environmental stress, many modern concrete structures deteriorate within decades. Yet parts of Hadrian's Wall have survived nearly 2 millennia. Scientific analysis of Roman mortar samples found mixtures containing lime, sand, clay, and volcanic components capable of producing unusual chemical reactions over time. Some microscopic studies identified crystalline formations that continue strengthening internal bonds centuries after the original construction. Modern researchers describe this phenomenon as a form of self-healing concrete. This discovery stunned material scientists because modern self-repairing concrete technologies only began serious development in the late 20th century. Researchers comparing Roman mortar to modern Portland cement found that some ancient formulas resist water penetration and chemical erosion more effectively over very long periods. In certain locations along Hadrian's Wall, the Romans also appeared to adapt mortar composition depending on local geology and moisture exposure. That level of environmental engineering should not have existed in frontier Britain during the 2nd century AD. Even the stone selection raises questions. Geological surveys show that Roman builders transported different stone types depending on expected climate stress. Dense sandstone was frequently used in wetter western regions, while lighter materials appeared elsewhere. This suggests Roman engineers possessed practical long-term knowledge of weathering behaviour centuries before modern geology formally existed. Another overlooked mystery lies underground. Excavations revealed sophisticated drainage layers beneath sections of Hadrian's Wall. Roman engineers constructed stone-packed foundations capable of redirecting groundwater away from structural pressure zones. In modern civil engineering, nearly identical principles are used to reduce frost heave, the destructive expansion caused when underground water freezes. This is extraordinary because freeze-thaw damage is one of the most dangerous long-term threats to stone architecture in cold climates. Many ancient civilizations built massive walls, but relatively few developed advanced subsurface drainage systems specifically designed for environmental survival over centuries. Archaeologists discovered that some foundation trenches reached surprising depths depending on local terrain stability. In marshy zones, additional compacted gravel layers were added to distribute weight more evenly. Modern geotechnical engineers studying the wall noted that several Roman solutions closely resemble contemporary stabilization methods used beneath highways and railways. The Romans may not have possessed modern physics equations, but they clearly understood how water, soil pressure, and seasonal temperature changes could destroy structures over time. And somehow, they engineered around those problems with astonishing effectiveness. Hadrian's Wall was never simply a wall. Every Roman mile stood a small fortification known as a mile castle, accompanied by observation towers positioned between them. The spacing was so standardized that researchers believe the system functioned as a high-speed communication network across northern Britain. Signal fires, smoke, reflective shields, and torch relays may have allowed warnings to travel across the frontier within minutes. Computer simulations conducted by military historians suggest that, under clear conditions, emergency signals could theoretically move from one side of the wall to the other, far faster than physical messengers travelling on horseback. The real mystery is how accurately the Romans positioned these towers. Visibility studies show that many towers maintained overlapping lines of sight despite difficult terrain. Achieving that level of visual coordination would require detailed topographic planning over enormous distances without aerial mapping technology. Some archaeologists believe Roman military engineers conducted systematic landscape analysis, using elevated scouting teams long before construction began. Others argue that astronomical alignment methods may also have played a role. What makes this even more remarkable is that Hadrian's Wall was connected to an enormous supply infrastructure behind the frontier. A military road called the Stane Gate linked forts and supply depots across the region. Warehouses, granaries, workshops, and barracks operated continuously to sustain thousands of troops stationed in hostile territory. Maintaining such a system required supply calculations, scheduling, transport coordination, and resource management on a scale comparable to early modern armies. One of the greatest unanswered questions is why Rome invested such immense resources into Hadrian's Wall in the first place. Traditional explanations describe it as a defensive barrier against northern tribes, but many historians now argue that the wall functioned more as a political and psychological boundary than a purely military structure. The wall contained controlled gates where merchants, travellers, and livestock could pass under Roman supervision. Archaeological evidence suggests taxation and trade monitoring occurred regularly along the frontier. In other words, Hadrian's Wall may have operated as a massive border control system rather than a simple fortification. Yet the mystery deepens when considering later Roman strategy. Only years after completing the wall, Rome pushed farther north and built another frontier, the Antonine Wall, before eventually abandoning it and returning south again. Why construct two gigantic frontier systems within such a short period? Some researchers believe the walls represented shifting imperial propaganda rather than military necessity. They projected Roman authority across the landscape itself. From the air, Hadrian's Wall would have appeared as an artificial scar cutting civilization from what Rome considered the unknown north. It was architecture designed not only to defend territory, but to psychologically dominate it. On the western coast of the Black Sea, beneath the modern Romanian city of Constanta, archaeologists uncovered the remains of Tomis, an ancient Greek colony founded in the 6th century BCE that later became one of Rome's most fortified maritime cities in Scythia Minor. Excavations intensified during the late 19th and early 20th centuries when construction workers repeatedly struck buried walls, tunnels and marble streets beneath the modern harbour district. What initially appeared to be an ordinary Roman port slowly revealed something far stranger. A coastal city built with engineering methods capable of surviving nearly 2,000 years of salt corrosion, seismic activity, freezing winters, and repeated invasions. The deeper researchers excavated, the more unusual the site became. Beneath modern Constanta, they found overlapping Greek, Roman, and Byzantine infrastructure, layered almost like an engineered machine evolving across centuries. Massive limestone walls still stand despite continuous exposure to Black Sea humidity. Underground water tunnels maintain gradients so precise that modern engineers measured deviations of only a few centimeters over hundreds of meters. Even more mysterious, sonar scans offshore detected submerged harbour structures built with stone locking systems rarely seen outside the greatest Roman maritime projects of the Mediterranean. Unlike Pompeii, which was frozen instantly by volcanic ash, or Alexandria, which disappeared rapidly beneath the sea, Tomis survived through constant adaptation. That survival itself became the mystery. One of the greatest mysteries surrounding Tomis is how its coastal infrastructure resisted environmental destruction for so long. Modern marine concrete often begins severe degradation after only 50 to 100 years due to chloride penetration, corrosion, and freeze-thaw damage. Yet sections of Tomis's harbour foundations and defensive walls have remained structurally recognisable after nearly 2,000 years, beside one of the most chemically aggressive environments in Europe. Geological surveys around Constanta reveal highly saline soils combined with intense seasonal temperature shifts. Winter temperatures can fall below freezing while summer heat rapidly expands surface materials. These cycles usually fracture ancient masonry over time. However, Roman mortar samples recovered at Tomis show evidence of hydraulic lime mixtures unusually resistant to water infiltration. Scientists comparing the mortar composition with Roman harbour concrete from Ostia and Caesarea Maritima discovered similar crystalline structures formed through long-term chemical reactions with seawater. These minerals, particularly calcium aluminum silicate hydrates, can actually strengthen concrete over centuries rather than weaken it. The problem is that Thomis lacked major local volcanic ash deposits, the pozzolanic ingredient normally required for this reaction. This raises a difficult question. Why transport specialized volcanic material hundreds of kilometers across the Black Sea, unless the Romans deliberately understood the chemistry required for long-term marine durability? Some researchers believe Thomis functioned as a strategic experimental outpost for frontier engineering. Others argue the Romans possessed far deeper practical material science knowledge than historians previously assumed. Modern sonar and underwater mapping have revealed linear stone formations extending beneath the harbour waters outside ancient Thomis. Several structures appear too geometrically aligned to be natural. Divers investigating portions of these submerged ruins documented large stone blocks fitted together with remarkable precision, some containing possible dovetail-style locking systems similar to those used in Alexandria and Caesarea. These underwater remains may represent sections of the original Roman port destroyed by earthquakes, shoreline collapse, or rising sea levels. Yet the engineering itself presents another puzzle. The Black Sea is not a calm inland basin like many Roman ports. Seasonal storms generate strong wave energy and shifting sediment pressure. Building durable harbour walls under those conditions would have required advanced knowledge of underwater stabilization. Comparisons with Caesarea Maritima in Israel are especially striking. There, Roman engineers created giant hydraulic concrete breakwaters by pouring volcanic ash mixtures directly into seawater using wooden forms. Thomis may have employed a related system adapted for colder climates and different coastal geology. If confirmed, this would place Thomis among the most technically advanced maritime engineering sites in the Roman world. Beneath modern Constanta lies a hidden labyrinth of ancient tunnels, reservoirs, drainage systems, and vaulted corridors. Many remain inaccessible or only partially mapped because modern urban construction sits directly above them. What astonishes engineers is the precision of the hydraulic planning. Roman aqueduct tunnels beneath Thomis maintained consistent water flow without pumps, relying entirely on gravitational gradients. Laser measurements conducted in several accessible sections showed incredibly small elevation errors, despite the tunnels being excavated nearly 2 millennia ago. Some vaulted corridors were constructed using alternating brick and stone pressure distribution patterns, similar to anti-seismic techniques later perfected in Byzantine architecture. This may explain why sections survived repeated earthquakes that damaged newer buildings above them. Humidity inside certain underground chambers remains unusually stable year-round. Archaeologists suspect the Romans intentionally designed airflow systems to regulate moisture and reduce structural decay. Comparable passive climate control principles appear in Persian qanats and underground storage complexes in Cappadocia. Yet Thomis combined these methods within a coastal urban environment, something rarely seen elsewhere in the Roman frontier provinces. Even today, large portions of the underground city remain sealed or unexplored. Roman bathhouses discovered at Thomis contain hypocaust heating systems specifically adapted for the brutal coastal winters of the Black Sea region. Standard Roman hypocausts used elevated floors supported by small pillars, allowing hot air from furnaces to circulate underneath rooms. But Thomis appears to have pushed this technology further. Archaeologists identified hollow wall bricks and multi-layer insulation chambers that significantly improved heat retention. Thermal simulations performed on reconstructed sections suggest these rooms could maintain stable temperatures far longer than conventional Roman bathhouses elsewhere in the empire. This is remarkable because fuel efficiency was essential in frontier regions where wood supplies were inconsistent. Some researchers estimate Thomis engineers reduced heat loss by up to 20–30% compared to standard Roman bath structures. The system resembles concepts found in modern thermal insulation engineering, yet these innovations appeared nearly 1,700 years before modern heating science formally understood convection and thermal retention. Why such advanced thermal optimization emerged specifically at Thomas remains unclear. Several streets and ceremonial structures in Thomas appear aligned with significant solar positions, particularly sunrise angles during solstices. Satellite measurements and archaeological mapping indicate certain axes deviate by only 1 or 2 degrees from astronomical targets. This level of orientation accuracy required careful observation and mathematical planning. Greek colonists already possessed advanced astronomical traditions, but Thomas suggests those systems continued evolving under Roman administration. Some historians believe the alignment served symbolic religious functions connected to Apollo or solar cults. Others argue it had practical value for seasonal navigation and harbour management. The mystery is not simply that Thomas used astronomy. Many ancient cities did. The mystery is how accurately these alignments were maintained despite centuries of rebuilding across multiple civilizations. Excavations at ruins at Tomis show repeated destruction followed by reconstruction using increasingly advanced materials. Greek stone masonry evolved into Roman hydraulic concrete, while later Byzantine builders introduced anti-seismic structures designed to absorb stress during earthquakes. Some Byzantine bricks even display better salt resistance than earlier Roman materials, suggesting centuries of continuous engineering improvement. Rather than remaining a static ancient city, Thomas may have functioned as a long-term technological adaptation zone, where multiple civilizations refined coastal survival techniques in one of Europe's harshest maritime environments. This challenges the idea that frontier cities were technologically inferior to Rome's core regions. In some ways, Thomas may have been an innovation center driven by environmental necessity. What do you think is still hidden beneath Thomas? Lost Roman technology, undiscovered tunnels, or an entire buried district no one has reached yet? Share your thoughts in the comments below.